So just to a brief feedback on yesterday, I so this is the first time for me and Philippe. We are doing this presentation, and I totally forgot to properly introduce myself. So just to put, just to do a little more context, I'm a thermal engineer, and I'm working in the same office as Philippe, who is a software developer, and is helping me develop software that with a small team of 6 people here in Strasbourg. And so today we will be presenting our software, Ktirio, and Philippe will be doing the presentation since he has a more technical knowledge about the software. Concerning the question from Volkan, yes, we will send the presentation. Maybe we just need a little bit of time just to add some text on the slide because, for example, yesterday I didn't put as much text and I was mostly speaking. So if you want a better presentation than what I showed you yesterday and with some notes that you can read, I will just need a little bit of time to add some text.
We will be uploading the slides, I think, on a website, the website of the repository of code where you did the exercises. So we will keep you informed, but I think we will publish it maybe on Friday or at the beginning of next week. And we will give you the link of the repository at the end of the day and tomorrow also.
So just a brief recap and Q&A from you. So if you have any question regarding yesterday's presentation, please feel free to ask. If you have any feedback, also feel free to ask in the chat. I'm glad to see you to see that you came back for today's presentation. And I don't see any question in the chat, so maybe we can start presentation. If we are a little early, as we did yesterday, we can still do the same thing and we can still answer some questions that you will ask during the day at the end of the day, if we have some time left. And I will let Philippe speak now.
So for today, we will present you the UB pilot of HiDALGO2 and its software Ktirio. So we'll do a general overview and we will see how the software is managed, how it is developed, what are the features in the software. Then I will present you some slides, and after at the end I will show you a demo in video, and I will also launch a simulation on Carolina node, and I will show you how we manipulate the data and the results. Then at the second part of the morning, we will do technical presentations about the weather data and some phenomena of the weather that are important to take into account when you are doing thermal simulations of buildings in cities. And we will do 2 exercises to manipulate those weather data. And then during the afternoon, we will do some exercises about optimization of a building. So we have prepared 3 cases of a building, and we will add difficulties at each cases. So it will be a simple building, but I think there are a lot of parameters to optimize, to try to find a good optimization of the energy consumptions. So we'll discover it later. And if we are earlier, maybe we can present the exercise at the end of the morning and start to work during the afternoon. Just precision, the exercises will be also on CodeSpace. So you can use the same repository that you used yesterday. And I will present it later, but you will find the exercise in the notebook folder, then in training day 2. And there are 4 notebooks, I think, so notebook about the weather exercises, and then the case studies of optimized building. So let's start with the presentation of Ktirio and UB pilots. So to give you a little bit of context, so the building sector accounts for approximately 40% of the final energy consumption and 36% of greenhouse gas emissions within the European Union. So in response, the EU has established ambitious targets. Under the Fit for 55 package, for example, the goal is legally binding a 55% reduction in net emissions by 2030. Also, France exemplifies this urgency with regulations like using the décret tertiaire in French. So it's a decree mandating a 30% energy reduction for commercial buildings by 2030. So to meet these targets, standard regulatory calculations are no longer sufficient. There is a rapidly growing demand for softwares that are doing dynamic thermal simulations to bridge the gap between compliance and actual building performances. So regulatory calculations rely on static and standardized scenario for compliance. On the other part, dynamic thermal simulations model the building's physical behavior under real conditions. So let's talk about the HiDALGO2 project a little bit. In the HiDALGO2 project, we aim to explore synergies between modeling, data acquisition, simulation, and data analysis, also visualization, while we improve the scalability of current and future HPC infrastructures. So we are doing that to provide highly scalable solutions capable of efficiently utilizing pre-exascale systems. So each HiDALGO2 pilot that you see on the right of the screen performs high performance computing and advanced simulations in their respective fields. So there are 5 pilots. So the Urban Air Project pilots is about improving air quality in urban agglomerations. So UAP project develops computational tools that model air quality, wind comfort, and urban planning related indicators at a very high spatial resolutions. So they are using CFD. About the renewable energy sources pilot, so this pilot models precise weather conditions for winds and photovoltaic farms and provide estimations of energy production for those energy sources. Also, as you may know, with the global warming, there are more and more wildfires in forests all around the world. So the wildfire pilot provides simulations of wild atmospheres interactions and smoke dispersion at several scales. And they aim at the assessment of risk and potential impacts over populated areas. Concerning the pilot about the matter transporting water, so this pilot develops numerical simulations to better understand the complex process of pollution transport in rivers. And so they are providing simulations to improve control and to do some preventions. As the same for wildfires, we want to develop tools to develop some prevention strategies to respond to the wildfires or some catastrophe in pollutions with in the rivers. Finally, so the urban building model pilot. So this is the pilot that we are developing in Strasbourg with Gwenole and other my colleagues. So the urban building model aims to offer simulation tools that can be used to predict energy consumptions of buildings. Also, we provide some indicators of the comfort and the quality of air in the buildings. And so we provide simulations at building scale and also at district and city scales. So let's go through the presentation of the pilot and its software, Ktirio. So Ktirio is a platform for building energy modeling and simulation that enable computing energy consumptions and losses in buildings, including comfort, as I said. So Ktirio is built on a large set of open source softwares, such as Fil++. So Fil++ is a library. Fil++ is a library in C++ language that is developed here at Simosis since I think 2009. So Fil++ is a comprehensive framework designed to tackle problems based on ODE and PDE, so ordinary differential equations and partial differential equations. So it uses modern C++. So we use C++ 17 standards, and we couple the utilization of our C++ code with Python. We use Python for manipulation, visualization, and we use the binding of Python to allow the users of Fil++ and Ktirio to be able to use the computation code written in C++ using Python. So for example, we used Python notebooks to do the exercise yesterday. We are developing some bindings in Python to be able to use Ktirio also in notebooks. So you can see some images of simulation or meshes. So let me present the workflow of Ktirio. So I will present each part more in details later through the entire presentation, but let's start with a quick descriptions. So on the left, you can see the input tools. So this is the inputs to generate the data, to generate the physical equations that we use to simulate the buildings. Also, we have a tool for containerizations to use the code in many HPC machines. So we use Aptainer and Docker. So Docker is I think, very famous in containerizations. Attainer is also for containerization, but it is very used in HPC computations. So we use Modelica also to develop our models. So Gwenole showed you yesterday a little bit of how we can use Modelica language using OpenModelica. For our part, we use Dimola, which is not a free software, but it helps us to build our models. We have the graphical user interface that I will show you after. So this is from this interface we can visualize the data, and we can create the data. So we use OpenStreetMap. So the user, you will see, can select every location in the world and build a mesh from that. We also have a version in the web. So we have a web user interface also. And then in the input tools, we have a website and a repository to do benchmarks. So to check if the application is well performed on your HPC machines. So then on the top of the workflow, you have the data. So we manage a lot of data. So there are some platforms that we use to manage the data sets. So we have CCAN, Girder, and Zenodo. Concerning the data we manipulate, we have GIS files. So GIS is for Geographical Information System. We have weather data. Simulators is about the models to simulate the physics into the buildings. We have scenarios. I will talk about it later. We have meshes, and also we have some data outputs. So we have reports, we have data for visualizations, and we have logs to see some details during the computation time of simulation. On the right, sorry. On the right, you can see the output tools. So Ktirio GUI is also an output tools because we use it for visualizations. We are developing some improvements to visualize some results in the GUI. We use ParaView, that you know, because we use it yesterday. Very useful to visualize 3D results. Field paper benchmarking. So as I said, so we use field paper benchmarking to trigger some benchmarks, to perform some benchmarks, especially when we are doing a release of our code. So field paper benchmarking has a website where we can visualize some results and performance of the computations. Then we have Ktirio Cases. So Ktirio Cases is also a website, and it is suited to visualize some graphics and metrics about the results of building simulation or city simulations. So we can see, for example, the graphics about energy consumptions. Then we use CFD visualization, but it is used with our partner UAP, the Urban Air Project. So we couple their tool of visualization to visualize some results of simulation, because we are developing a coupling between the UAP pilot and the UB pilot. I will talk a little bit about this coupling later. And then you have orchestrations. We use different orchestration tools such as Matso, QCG. We use GitHub, so we use GitHub Actions and the CI of GitHub to trigger the workflows and to follow if every part of the integrations is well done. At the center, we have the Ktirio Urban Building code, so the software that contains the computations. And then we can trigger, when we launch simulations on Euro HPC systems. So you can see in blue, different European machines, and in red, or in light red, Jupyter and Alice Recoq are French supercomputers. So we use, so it is written HPC as a service. So we provide simulations of buildings using HPC machines as a service. So let's go through this different part in details. So first of all, I will present you the GUI. So Ktirio GUI is a graphical user interface written in Qt that allows preparing the data for the urban building packet. So it allows us to generate the GIS datasets, the meshes. Also, we can visualize the mesh on the GUI. We can also generate weather data. So we have different menu on the top of the GUI. So here, under my cursor, this is a menu to generate the weather that I want. Also, you have a tool to create scenarios. So we have developed some basic scenarios with the reference we have in France, but we are we continue to improve the tool, and we are developing some upgrades for scenarios so that the user will be able to create his own scenarios. So also from this tool, we can upload datasets on data platforms, and we can launch simulations using Euro HPC computers or other computers using Slurm. I will explain. Slurm is a software used to manage and launch simulations in Europe in HPC machines. Also, we enable visualizations. So to generate some of our data, such as the GIS file and meshes file, we use OpenStreetMap, which is like Google Map, but it is open source and user can contribute. We request OpenStreetMap using APIs such as Mapbox and Overpass. So now let's go through the data. So let me present the input data. So we use different file formats such as mesh formats, JSON formats, CSV format, and FMU format. FMU is for the physical equations and building models. So it's like the models you use in the exercise yesterday, but it is more complex with 1,000 equations for each buildings. So first of all, we have a GIS. So GIS is for the locations of the buildings. It's about basic informations, and from the GIS, we can build mesh using other tools. So mesh is about the geometry of the buildings and the environment. We have weather data. So not this afternoon, but later in the morning, we will present which weather data we use, but with some temperatures, wind conditions, etc. And also we have the scenarios, so scenarios about the instructions of heating, ventilation, cooling, and other things. So the instructions in the buildings. So the set points of heating in each building, for example, at each time step. So also we have the output data. So we use also JSON format, HDF5 format for large storage of results. HDF5 is a file format suitable for HPC computations. And we use also unsignable format for visualization. So I put you some graphics we use for benchmarks. There you have a visualization using ParaView, so we can see solar shadings. And I think it's about the bottom visualization is about the heating flow or the energy consumed per building. And so we have the reports, the graphics to show some curves, and we upload it on the website Ktirio Cases. So to go in details about each data, so GIS is for geographical information systems. So which data we can retrieve in GIS? So we have the coordinates in latitude and longitude of the center of the simulations and the coordinates of the buildings. So we can store basically the I don't remember the vertices and of the buildings. We have the coordinates in the project plane of the simulations. We can have the height of each building, its altitude, the type of buildings. So in OpenStreetMap, there are informations about the type of the buildings, if it is a house, a farm, a school, an office. So it can be very useful when we launch simulation using scenarios to have the type of the buildings. Because, for example, if you want to heat during the day, you will not heat the same way in schools and hospitals than in your houses. So because a lot of people are not in their apartments or houses during the day because they work, so they will lower the instruction of heating, set point of heating, compared to school where we want to heat during the day from 7 a.m. to 7 p.m., for example. So we have also identification numbers, roof shapes, and some other details. But that's all. So as I mentioned earlier, we use OpenStreetMap to collect information. So quick recap, OpenStreetMap is a free editable map of a world created by a community of mappers. So it is a collaborative project and it is open source. So it relies on local knowledge. So anyone can use OpenStreetMap and update some data. So contributors are especially encouraged to add informations about the areas they know the best, such as where they live or where they work. So yeah, OpenStreetMap is entirely open source and accessible. So let's go through the meshes. So, excuse me. So in the mesh, we want to integrate all components such as buildings, but also the environment, such as the terrain and the vegetations, the parks, the trees. We will see why. We want to ensure the conformity and watertightness of robust simulations. So when we are building our meshes, we assign markers to attribute types such as building, tree, and subtype, a type of tree. If the part of the tree, the trunk, the leaves. Also for buildings, we mark the walls, the roof, the stories. If an element is part of the mesh of the ground floor or the second floor. So to create mesh, we use Ktirio that we are developing. So it is a special tool for generating and adapting meshes for 3D cities models. And it is based on Seagull. So Seagull is an open source software project that provides easy access to efficient and reliable geometric algorithms. And it is a C++ library. Seagull is used in various areas needing geometric computations, such as geographic information systems like us, but also computer graphics or robotics, for example. So concerning the building modeling, we use a multi-fidelity representation of our building models. So we have three level of descriptions. We have load 0, which correspond to oriented bounding boxes. So it's basically a perpendicular form that bound the real building. Then we have the level of description 1, which is a multi-polygon extrusions from the ground trace of each buildings. Also in load 1, we can add windows, roofs, and we have level of description 2. So level of description 1 and 0 are based from the OpenStreetMap data that we retrieve. Level of description 2 is based on BIM data and EFC formats. So we don't really use every week the load 2 description because we need files with a lot of descriptions. So it is more suitable when particular an enterprise wants to do a simulation of its own building in details. In this case, we will use load 2 format. But it is in current development. We are, in the case of HiDALGO2 project, we focus more on city-scale simulations using load 0 and load 1 simulations, load 1 building models. Okay, so to continue, on the left of the slide, you can see the options menu for buildings that is currently present in the graphical user interface. So we can choose the level of details, and we can choose to include stories. So if we don't use these options, we have less detailed meshes for each buildings. But if we use these options, we have triangles and elements in our meshes to describe each stories of each building. Then we also include roof shape. So we have some information about the roof shape in in the open source datas that are accessible, but sometimes there are not the informations about the roof shapes. So sometimes the information is missing. So we use some algorithm to determine by default some roof shapes. We know that, for example, the flat roof, the gable roof, and the hipped roof are very used, and they are the main roof shapes that are used in every buildings in Europe. So you can see on the right visualization using GMSH. That's it. So then we have modelization, the meshes of the environment. So why it is useful to mesh the environment? So they are essential to accurately represent to do better simulations, because the environment is very important. We want to modelize the topography around the buildings, the vegetation and the infrastructures, because it can drive some dynamics about the heat exchange and the airflows. Also, the environment creates shading, so it is very important to take into account the environment, because the environment can block the solar radiations, and it has a significant impact of the heating of the buildings and the energy consumptions per consequence. Also, we don't modelize everything, but we have some effect of cooling with vegetations. So we have also effect of cooling and albedo effects with the parks, with the rivers, and with the city infrastructures. Some materials, for example, for the roads, can heat a lot. So we are currently improving our physical simulation to take into account those details. But for the moment, for example, we don't take into account different ground temperature in every location of the cities. We have the same temperature, but in the future, we will take into account different temperature depending on the materials of the ground. So to modelize the terrain and to create its meshes, so as I mentioned earlier, we use Seagull. Basically, we construct isolines, and then we do triangulations between the isolines, and then we simplify to construct our terrain meshes. So you can see an image of a terrain. It's in the mountain. I put a small image. It's not there is not a big radius, but you can see the difference in elevations. Then, so we have the vegetation modeling. So as I mentioned earlier, it is very important to simulate the environmental impacts for solar shading, for example, and the solar mask effects on buildings. We currently we have a library to support those meshes of vegetation. Currently, in our simulations, we support 3 types of trees. So we can see on the bottom right 1 type of tree. I don't remember the name, sorry. And I put the option menu for vegetation in the GUI. So in the same way for buildings, we can choose the level of details of the trees we want for the meshes of vegetation in the simulation. So basically, we also have a level of descriptions. So load 0 is simple geometric shape. Then load level of description 2 is a realistic shape, but a little bit simplified, of course. But we can see we have the leaves in more details. And level of description 1 is a simplifications of level of description 2, and we execute an alpha wrapping on the load 2 models. So about the weather, we use weather data from stations or forecasting models, such as temperature at 2 meters of the ground, the wind conditions, the solar radiations. And so we have different resolutions. We can use different resolutions of weather and precisions. So when we use weather data from stations, we have the same weather inputs for 10 kilometers squared or 20 kilometers squared. But when we use forecasting models, we can obtain more precisions, and we can obtain weather data for each kilometer squared. So it can be very useful because you will see later in the presentations that the temperature, especially in the cities and their environments, are not equal. So it is very interesting to use more precise weather models. We can also adjust step time, so we can retrieve weather data for every 15 minutes or a half of an hour or 1 hour or 2 hours. So about scenarios, so we have occupancy scenarios that are essential for realistic energy simulations. So the scenarios are the instructions of heating, cooling, and ventilations in the buildings. So it defines the different set points by building category. So if the heating set point is 20 degrees Celsius, so the building and its heating system will heat until it reach the temperature of 20 degrees in the interior of the building. And then the cooling is the same, but it's the contrary if the temperature is above, for example, 28 degrees. So we will activate the cooling to reduce the temperature inside the buildings. So we take also into account ventilations, and we are improving the scenarios to take into account the internal gains, such the appliances heat sources and the human heat sources, because it can really affect the temperature inside the buildings. So basically, we define an instruction for per each time step. And so, as I mentioned earlier, we have created some basic scenarios that every user can use, but we are currently developing and improving it for the usability to be able to create scenarios using a menu of scenario edition. Then we have physical models in the FMU format. So it is based on Modelica and Field++. So we use multi-zone models. I put you some structure informations we can retrieve in our models, such as the material, of course, roof shape, the dimensions, We have some inputs about the shading for each surface to take into account the solar shading affecting the reception of solar radiations. We have comfort indicators, weather input, of course, and also some heating and cooling systems. We modelize also windows and pollutants. I think I forgot some other details, but you have the idea of what equations of physics we can retrieve in our inside the building models, physical building models. So now I will talk a little bit about the output tools and visualization. I will just drink some tea. Give me 10 seconds. So about visualization and output tools. So we use visualization using ParaView to visualize the result in 3 dimensions. So here is an example of a simulation using load zero models. So on the left, you can see the temperature of the exterior surfaces of each buildings. On the right, you can see the interior temperature of the buildings. We can also visualize the shadings created by buildings and environment, so created by the mesh. So we can see, so this is a mesh of Strasbourg using load 1 meshes. I will talk a little bit about solar computations later in the presentations. Using ParaView, we can also visualize some heat flow exchange. We can also visualize the energy consumptions. And maybe some more things, maybe I forgot, but basically you have the idea. So we visualize heat flow exchange, temperatures inside the buildings, on the surface, the shadings, and so on. Then we have the reports. So we have a website where we can select results for some cities we have simulated. So basically we put about on the website, currently there are 10 cities results. It's the cities where each pilot and each team of working teams in HiDALGO2 are located. So basically, which data are visualized? So we have graphics also of temperatures, for example, for buildings or the mean at city scales. We can also visualize the weather, such like the graphics we will manipulate later. We have some statistics about the types of the buildings, the mean of the height of the buildings in the cities, the mean of the surfaces, the distribution of the surfaces, etc. We have also graphics about energy consumptions, heating curves, and so on. So also in the output tools, we have results on a website called FUPP benchmarking. So here you have an example what you can find on the website. So we have a list of supercomputers. We can find Discoverer, Gaia. Gaia, it's in Strasbourg. Carolina, as you may know, Lumi, Meluxina. So we perform benchmark on these supercomputers, and we compute some graphics to see the results. So here is an example of the scenarios of benchmark we have performed. So we have benchmark Paris and Berlin on one day with a different radius. So more the radius increase, more we have buildings to simulate. And we perform some benchmark with different type of nodes to see the accelerations of computations or identify some bottlenecks and some problems. So on the left, you can see some relative performance of different computation steps. So you have the post-process, the initializations, the simulations of the Ktirio Urban Building simulations, and we can retrieve some others graphics. So then let's talk about the orchestrations and the use of HPC machines. So basically, we can trigger computations on HPC machines with several tools. So using the GUI, we can launch simulations on HPC machines. We can also trigger directly from the machines simulations of Ktirio. I will show you later a demonstration on Carolina. So then we have GitHub Actions and workflows to follow if the computation steps are doing well or not. We deploy the simulations on the HPC machines, and we upload the results on data management platform to visualize the results using the website results with the benchmarking website and the Ktirio cases website. So we use Slurm to launch simulations and to schedule jobs on Europe HPC machines. So Slurm is an open source workload manager that schedules jobs and allocates resources across clusters of supercomputers. So it optimizes computing power by managing job queues, assigning specific compute nodes to users, and monitoring the execution of their tasks. So here you can see a schematic and a workflow of submissions on HPC clusters. So basically, when we are doing a release of Ktirio Urban Building, we create an obtainer image and we test and benchmark the applications on different Euro HPC machines. So Obtainer is an open source container platform which is designed for secure HPC environments. So Obtainer excels in multi-user Linux systems such as HPC cluster, and it offers features similar to Docker. And it includes compatibility with most Docker image, and for computation on your HPC machines, it adds security and portability requirements that are required for HPC computations. So you see when we create, we trigger the workflow or we create a new obtainer image, we trigger some checks about if application and the image is correct, if the datasets are correct, if the HPC runners are available, and then we trigger on your HPC machines. Then we upload the results on the different websites I showed you before. About the monitoring status, so we can monitor the different status using CI and GitHub Actions. Earlier this year in March, our team did a training sessions about containerizations continuous integration, continuous development, and benchmarking solution for HPC. So if you're interested, the recordings are probably available. I don't know where, but maybe Lucy can tell us where it can be available. We can talk about it later. To perform simulations on big supercomputers and do parallel computations, it is very important to have partitioning strategies. So we have to, when we are launching simulations of Ktirio and building city simulations, we want to distribute the terrain, the buildings, the vegetation entities efficiently for HPC applications. Because as you may know, if you don't distribute your work equally, you will have problem because some CPU will wait and will not be used completely, where other CPUs will be overloaded. So it's very important to partition correct equally the mesh to perform useful and good simulations using a lot of nodes. So we want to ensure that spatial partitionings so that nearby objects remain within the same partition for computational coherence. So we have some different algorithm of partitioning based on the mesh agency graphs and the leveraging mesh conformity to optimize performance. So on the right, you can see different distributions on a mesh. Also, I wanted to talk about how we compute the shading masks. So to define the shading mask, because we will visualize it on ParaView later, and you can visualize it currently on the slides. Shading mask is quantify the percentage of block solar radiation for a building surface. So it depends on the sun positions. So here you have visualization of a shading mask of one surface. So when it is white, we have no obstructions of the solar radiations, and when it is black, we have total obstructions, and we have, of course, we can obtain values between 0 and 1. Imagine a building with trees around, but some suns, some ray of the suns can go across the leaves and can touch your building. So it can be, a building can be, of course, partially obstructed. So we use Monte Carlo method and ray tracing techniques to compute those solar masks, and we compute it in parallel, of course. So basically, using ray tracing methods, we can create like 1,000 of ray in direction of the sun, and at the end we are looking if some rays have been intercepted or blocked due to environment or not. Now let's do a demo. So I will start simulations using a Carolina node, and I will show you a demo video. So I think I can start to launch a simulation using Carolina. Then when the simulation is launched and we are waiting the results, we will be watching the video, and after we come back to see the results of the simulation we have launched on Carolina. So give me 1 minute. So if you have any questions, I don't know, I don't see the chat. Maybe you can check the chat if there is some questions. So here is my Visual Studio Code window. I'm currently connected on Carolina. So first of all, I will open the GUI of Ktirio. Okay, there it is. So here is the graphical user interface of Ktirio. So basically, we can create a new project. Create. Okay. So on the top, as I mentioned, you have different menu. We will not use every menu for the moment. On the left, you can see some of your elements of your scene. And we have a menu properties that will be useful later. So first of all, I will start a new simulation. So I create a simulation for using Ktirio Urban Building to do simulation of a district or a city. So then I click on next. So there it is, the map of OpenStreetMap. So we can choose locations. So for example, if I type Prague, I can choose where to put my cursor. I can move it. Yep. So I don't have a right button. NP. But I can enter locations in Praha. Maybe I have some. I don't know the address, some address in Prague, so it will not work. But if I do Strasbourg, I can put the address of the lab where we're working. So if I type the street, it's fine. Okay, this is okay. So our lab is located there. So it is in the University of Strasbourg. So basically, I will do a simulation of Strasbourg, so I can take the basic location when I type Strasbourg on the map. So then I have a cursor, which is on the place Kléber. So if I do next, I can choose the radius of the simulations of the section of a region I want to simulate. So we will not take a big radius for a moment. You see, you can put 5 kilometers radius, for example. So it will be a 10 kilometers diameter, but it will be quite big. And if you want to visualize without some lags and freeze, I think we will do just a simple simulations. We will take a radius of 500 meters. So it perfects, it take into account the cathedral. Let's go for it. So you can see the coordinates of the center of the simulations. Then we can do next. And then we can choose options for meshes. So we have a predefined load 0 and load 1 setup, but if we want, we can add setup. I will not do it for the moment. So we basically can choose between those options. So we can use elevations of the terrain. We can show the water layers for the rivers, etc. And for the buildings, as I mentioned in the presentation, in the slides, we can choose if we want load 0 or load 1 for the buildings. If we want to include stories, we can choose it. For vegetation, we can also choose the level of details. And for load 1, for the preset, with load 1, we can do the same. So I will create a preset for load 0 and load 1. I will keep it simple. I will not use all options. So then we do next. So here it's a menu for the visualization in the GUI. So if I enable this, I will have the load 0 mesh that will be displayed on the GUI. So I will just enable visualization for load 1. So then we create the mesh. So it can take some times. So let me check for Carolina the reservations. Okay, so for Thursday, I have this reservation. Okay, nope. So we can see that the construction of the meshes are currently working. We have the progress bar on the right. Oh, perfect. So it starts to appear. It's almost finished, but we can start to visualize. So yeah. So here we have level of description 1 for buildings, and we have level of description 0 for trees, but it's quite interesting. So I can navigate in the mesh using my cursor. I can zoom. So here I think we have a sample of maybe 2,000 of buildings, maybe 1,000. So you can visualize the cathedral. We will see in the simulations that it will cause a lot of shadings. So I put some vegetations. I didn't put the elevation of terrain. But yeah, so now the dataset is generated. So I click on new simulations, and I can update the input data. So we have a progress bar, it's done, and I can export the data. So here I have the geographic data, the weather data, the scenarios, and the cube simulation setups. I think it's a config file to launch the simulation. So I can click on next. And so there are the files that I will export. So we have different scenarios, the mesh load 0, the mesh load 1, and the JSON, the GIS, geographical informations, and the weather data. So I can click on exports. So I can choose between my own computers, or the remote data platform. So I can put Girder, for example. We have a server at Unistra, and I can put it like this For example, I can choose folder. Let me show you an example if I put it on Girder. For example, so here I have website of Girder, and so I can choose. I created a folder called demo, and for example, I can take the ID and I can upload the data on this data platform. So I do export. We have a progress bar on the bottom right, and we have mentioned that the export is a success. So then if I come back to Girder, I can reload, and there it is. I have some of the data I need to launch a simulation. Okay, so let's launch a simulations on a Carolina node. So I have some presets. So I did the same setup yesterday to prepare it. So I have some data. So this is the same data that I have exported on Girder. So I put it on Carolina because if I if I if I don't put on Carolina, it will be slower because the downloading the data from Girder will take times in Carolina, but we can totally launch simulations and download data from data management platforms and websites. So here you can see we have the mesh load 0, mesh load 1. We have different scenarios. I have a config file where I can choose the time, the start time of the simulation and the stop time. I can choose the step time also. So here it is in seconds. So it corresponds to 1 hour. Here it's approximately, I think it's 1 week. So I will simulate 7 days. It will start in January because my weather data start in January. So 0, I think it corresponds to the 1st of January. And I think it should be the meteor 2025. So I can put the path, the relative path of the G-Spy, the mesh I want to use. So we will be running simple simulation using level of description 0. We have the weathers, the scenarios, extra. So I will create a new output data folder, and I will take my bash script using Slurm. So there it is. So we will use the dataset for Strasbourg using 500 meters radius, so 1 kilometer diameters. So here using Slurm, I can define the job name. So we will call it Ktirio Urban Building. The number of tasks, we can put 128, or just, I think, 664 would be sufficient. I will have 1 node because I have a reservation with 1 node. CPU part task 1. So here, some files of logs I can watch, and that's it. So I put my accounts. So I indicate that the node is exclusive for me during the computation. And so this is my reservation. So I have put the obtainer image of Ktirio, of Ktirio Urban Building. And I will use it to launch the executable of Ktirio. So here I put data, okay, in a new folder. I will use as input every input I put there. No, not input, but yeah. So I think we will use maybe headers. Okay, so that's it. So it is ready. Strasbourg config. So let's launch simulation. So I have no jobs that is running currently. So if I execute the program, okay. So it started, I think. Okay, so here's the basic logs you can find when we are launching a simulation. So now, okay, so I have 1,536 buildings. So the simulation is starting. So it's loading the mesh. So let's check, let's the simulation be running, and I will show you a demo in video, and then we will come back for the simulations and we will see the result in Paraview. So let's see the demo video. Okay, so we have a video. I can launch it. So here is the graphical user interface I showed you. So the user can put his login and his password. So okay, here he has the super admin role, and I think, okay. So the user is connected. He will check in the settings if he has some tokens to use the different APIs. So if we want to use Girder, we have to have an account or a token to a Girder server. For CCAN is the same. To run Ktirio, we need a Mapbox token because Mapbox is an API that we use to interact with OpenStreetMap. So we need a Mapbox item to create the meshes. So let's start a new project, like as I did before. So we will simulate in this video the city of Luxembourg. So the user enter Luxembourg in the research bar, and okay, so we select a radius. So we have a 2 kilometers radius, and we have an address. We have an address is automatically attributed. So here we choose the different options. So here we have created a simulation, a mesh, sorry, with the elevation of the terrain, the water layer, the roads, and we are currently selecting the level of descriptions of the buildings and vegetations. So here we have a skip because it can take a little bit of time to generate everything. So here we can see the generation in live of the mesh. So Here we can see we can explore the mesh, so you can see a river. You can see we have the elevation of the terrain. In black, we can see the roads and so the buildings. So here is not flat. We have the elevation. So we have different type of visualization in the settings. Okay, so now we have the simulation setup, so it is the same, but here we will be launching a simulation using directly the button from the GUI. So here we select the building type of models and the building heaters. So we have different type of heating systems. Here we have ideal heaters, heat converters, or regular heaters. So we can launch a deterministic simulation using one of those heaters. So here we selected boiler, we have enabled the solar shadings, and we can choose in the calendar the time of simulation. So here we have a start time, so the 1st of January in 2023, and the end, we put the end of March. So we have a 3-month simulation. We can choose time step. Here we put 2 hours. We can choose to generate 3D visualization. So the 3D visualization is the export to visualize on PowerView. Which can generate a simulation report. The report is in a JSON format, and it's that file that we use to create the graphics. So then we export. So the user is doing the same, but there we choose Sican, not Girder. No, I need to have a rollback. Okay. Oh, okay, Sican. So Sican is a data platform used by HiDALGO2 project. Girder is a data platform, but we only use it. Not all the pilots use it, but just us, as I know. Okay, so we select the location of export. So Sican. We can name the datasets. We can choose a license, and we can choose the visibility if we want the dataset to be private or public, and we can put a number of the version. So let's do the export. Export is a success. So here we are in Sican. So you see it's different from Girder, and as the same way I showed you in Girder. Okay, not a problem. No, it's fine. Okay. So it's different from Girder, but it does the same job, and we have different data sets. So here we have a dataset Cube Luxembourg simulation, and if we enter in this folder or item, you can find every input data that we have generated, same data that I have generated before. So here is the menu to launch a simulation from the GUI. So we can choose the host. So sorry. So we can choose the HPC machines. Yeah, so you can see the list of some HPC machines. So Gaia is not HPC machines computer, but it only has 6 nodes. But we can see Euro HPC machines such as Carolina. We can select the computing resources, so the number of nodes and the number of tasks per node. Then we choose to export. the benchmark, the simulation report, and we can put an execution time limit. Then when we have launched the simulation, it triggers a workflow on GitHub Actions. And you can see it pulled the obtainer image of Cube, and then it downloaded the dataset and launched the simulation. So when the entire simulation is done, so you see the simulation took a little bit of time. I can see 4 hours. Up. Okay. So here you have the time of execution of each task in the GitHub Actions CI. Okay. Let's go play. Then we have we can export on Ktirio cases. So we have a link directly in the GUI to visualize the different graphics on a website. So it is the first version, but of course the graphics will be improved. I think you will see the graphics that we will use in the exercise are a little bit improved. So yeah, it's in continuous development. So then we can export the simulation results. So it's in a zip archive, and then you have different results. So yeah, it goes really fast, but here we open the PowerView file to visualize the results. So here it's the results for Luxembourg with a diameter of 4 kilometers. We can apply filters. I will do the same after. So here we can see a comfort indicator, another one, the curve flow cooling and heating. We can see the distribution, the partition of the simulations of building. Oh, oh. Okay, I can advance. So yeah, and we can adjust the colors. We can adjust the y-axis. Okay, so here we have another demo, but from the web user interface. So we open it from, I think, the HiDALGO2 dashboard, where we can retrieve all pilots applications. We launch the web user interface of Ktirio, and we can do the same. So basically, it's the same. We can choose the options, and we can generate the same as before, but the web user interface. That's it. So here it's from the HiDALGO2 platform. We can select the Attendees image, the resource, and launch a simulation instance. It basically does the same. So let's finish it, export. And at the end of the video, we have an example of a large-scale simulation. So here is a visualization of the results of simulation of Paris, the capital of France, with 10 kilometers radius, maybe 20 kilometer diameters, or maybe 10 kilometer diameters, I'm not sure. But here you can see the large-scale simulations with some comfort indicators at the top and the consumption of energy at the bottom left and the temperature inside the buildings. Okay, that's it for the video. Okay, so let's see if we have finished the simulation. Yeah, perfect. Yeah. So it's a quite small data set, so it went relatively fast. So in the logs, we can see the loading of the meshes, the creation of the partitioning, the use of different models, physical models for building simulations. And then we have the time step with the details of the time that the computation time for each step of the simulation. So we have the updates of the position of the sun. We have so the execution and computation of the solar mask, sorry. The execution of the time step of the buildings. We have also step to export the outputs and to write the reports through the simulation. So we have details for each time steps, and if I go at the end, yeah, the simulation is done, and we can retrieve some of the informations about the files. So now my output data folder is full with the results. And for example, I can go in instances. Here I can find the report JSON that can be used to create the graphics. But here I want to download the power view files. So I go in node 0, export. So here I have exports. I can perform download. Let's go. Let's create a new folder. Demo Bulding up. Wait, and I will download the export there. So I can start to open PowerView. Okay, there it is. We just have to wait a little bit for the download to perform. I think it will take 1 or 2 minutes. Okay, it's finished. Perfect. So let's open file. Okay, so I go to Carolina folder, demo Carolina, export, and I can open file. Then we go and choose apply. Okay, perfect. So here, so I will select PIDs for partition. I will use vertical composite index. So I have different elements. So you can see I have the buildings in blue in load 0. So the cathedral is quite ugly, but it's not very important. We can see in red the vegetation and the terrain in light gray. Okay, so first I will apply a filter, extract block. Yeah, that's it. So I will just show the building and vegetation, and I choose Y. Okay. Then we can visualize, for example, the solar shadings, solar shading cliff. So we can duplicate here. So let's change the colors. We'll put X-ray. All right. Then we can rescale to have every values that we can have during the simulation. So let's wait a little bit. Okay, perfect. So the value goes from 0 to 1. So 1, we don't receive solar radiations in black, and 0, we receive solar radiations. It varies, of course. Okay, so let's play. So yeah, so it starts. So we start at midnight. So of course, here it's a night, so it stay in black. But here we arrive at, I don't know, 8 a.m. or 9 a.m. And so we can deduce that the sun, the east, is probably there on the right, and we can observe the surfaces that receive shadings and the others that are not receiving shadings of solar radiation. Sorry, it's the contrary. So here, with the mesh, the big load zero mesh, the bounding box of the cathedral, it creates a big shading zone. So I can run the simulation. So with the visualization of the solar shadings, we can observe the trajectory of the sun too. Okay. So also we can see the temperature on exterior surface. So here I have I performed a simulation with ideal heaters, so it would not be very interesting to observe this value, but if we can observe the Q-flow heating, it's the value of the heat flux necessary to heat at the needed temperatures of the buildings. So I can rescale. So this rescale needs yeah, I will change the color. Let's choose, for example, this one. Okay, and then I can, of course, the values can be really big, but because there are just one or two big buildings, but I will put my own data scaling, my range. So let's just put on this value. And so there, if I start, you can see the actual heating of the buildings at each time steps. So here we just observe with these many colors that the heating of buildings are very active, and it depends on the condition of the weather, the exterior temperature, the solar radiation received. So the heating needed is different at each time step. Then we can observe temperature interior, so it will not vary a lot, I think, with this sample. So it's approximately at, I think, 19 degrees Celsius. But I think the instructions are not the same for every buildings. We can see during the night or the day, I'm not sure. Some buildings have to heat at 18 degrees, the others at 19 degrees. I can change the color too. So yeah, that's all for the demo. So I hope you enjoy it and you understand more what we are doing in the project HiDALGO2. I hope it was pleasant to discover it. If you have any question, please ask. We will respond it after the coffee break. I think, yeah. Yeah, we can start the coffee break now, and we can come back in 20 minutes at 11 a.m. and 5 minutes, if it's good for you. So let's continue the presentation. I will share my screen very soon. Okay, so let's continue with the presentation about the weather data manipulations. So let's go deep in how we compute weather data when we are using Ktirio Urban Building simulations. So I put the workflow again. So about the meteorological data. So we have this schematic with different type of weathers we use. So basically, we use observational weather data from weather stations using the API of OpenMeteo. So it gives us a lot of data inputs, but it's the same input for approximately 10 kilometers around, or maybe more. It depends on the locations of the weather's meteos stations. But we are doing some coupling with our partners in HiDALGO2. So we are doing a coupling with wildfires pilots because and the MTG, so Meteor Grids team. So using MTG, they can create and give forecasts past or future weather data at a higher resolution. So here you can see on the screen, you have the image, so the radius when we use OpenMeteo, a circle, concerning the mesoscale forecast model that we use from MTG. We have a grid, and we can change the resolutions from 1 kilometer square to 2 kilometers square, or 3, 4. And so we have specific and unique meteo datas every squared of the grid, of the 2D grid. So this is a coupling in work in progress. So we have to, So we have to integrate those utilization of data in our simulation code. So we will attribute a specific meteo input for every buildings using interpolations with all the data we have in the grid, in the 2D grid. Part of the coupling will be to improve the Ktirio graphical user interface. If I open it again, let's go software. So let's open Ktirio GUI. Ktirio GUI, when you create a project, you have this button where you can create weather data. So we can, excuse me. We can choose and interact with OpenMeteo using this menu, and we can choose the data we want. We will improve through our coupling with the MTG team with another section where we will have a button to download weather data using Meteo Grid. So it's a work in progress. It will be improving the GUI. And that's it for this coupling. I will show you. Oh, I will show you. Oh, I want to close GUI. Okay. Up. I will show you in the next slides an example of a type of heat map we can have with those kind of 2D grid. Then we have a coupling with the UAP project. So UAP are computing air pollutions and some weather conditions in a city, and they are doing CFD, computational fluid dynamics. We can exchange, so it's a coupling in progress too. We can exchange some data like the weather, not the weather, sorry, excuse me, the wind. So the wind conditions of the speed of the wind and the direction of the wind at a very small scale, like every 5 meters, for example, we can have different data inputs for the wind. In exchange, also, because this is a coupling in the two ways, so UAP gives us some weather data, and also we give to them some pollutions produced by the buildings. So the building produce pollution at the creation when it is built, but also, of course, when we use heating systems or other intelligent systems. So we exchange some data about the pollutants produced by the buildings. Okay, so let's talk about the meteorological data types. So in this section, we distinguish between 4 categories of meteorological data and climate informations relevant to building physics, especially for modeling temperature, radiations, and energy performances. So first of all, you have historical data. So historical data correspond to past observations, weather station measurements. They provide long-term records of outdoor temperature, solar irradiance, humidity, wind speed, and so on. We have reference data. So reference data provide standardized climatologic normals, typically 30 years average, it is used to define conditions for simulations. For example, we usually dimension the power of heating systems by taking the worst minimum temperature over the last 30 years. So these normals can be turned into specific derived datasets for building physics, such as typical meteorological year files or test reference years. So such files are constructed by selecting representative months, often based on statistical criteria, such as minimal deviation from long-term average, and assembling them into a synthetic climatological realistic year. Other variants exist, each tailored to slightly different modeling needs. For example, so as I mentioned before, the HVAC sizing for heating, ventilation, and cooling. So for long-term performance estimation also, for solar yield analysis, etc. So then we have the short-term forecasts. So we rely on numerical weather prediction models, which use the current atmospheric state as input and simulate fluid dynamics, radiative transfer, and thermodynamics to predict change over hours to days. So in building applications, these forecasts are useful for model predictive control, demand forecasting, and adapting HVAC strategies, where weather variables directly impact control decisions. So last but not least, the IPCC, so Intergovernmental Panel on Climate Change, scale projections. So the IPCC scale projections. It refers to scenario based on climate projections, which explore how climate variables may evolve depending on different greenhouse gas concentrations pathways. These projections are driven by emission scenarios called SSPs. So the initials are for shared socioeconomic pathways, which describe plausible trajectories of population, energy use, land use, economic development, and mitigation efforts. So each scenario feeds into global climate models that solve large-scale equations of atmospheric physics, radiative transfer, also ocean-atmosphere coupling, and biogeochemical cycles. To give you an example, under a high emission scenario, such as the scenario SSP5 8.5, models consistently project a strong increase in mean temperatures and more frequent extreme heat events by the end of the century. So these conditions strongly impact cooling demand, overheating risks, and envelope performance. So to talk a little bit about the preparation of weather data via Ktirio GUI, as I showed you before, we have menu and we can interact with OpenMeteo and select the weather variables that we need for the simulations. We also create other files, so we can use one meteo file from the station, but also we can create several. We can choose the locations of this weather, like we did to select cities to simulate. And we can choose every variables that we need. So a total of 36 weather parameters are available. And we use approximately 8 or 9 parameters for building energy simulations. So about I go first. I go this slide first. So in building simulations, we use here we use those parameters. So we have air temperature at 2 meters above ground. We have relative humidity at 2 meters. We have a wind speed at 2 meters from the ground, above the ground. We have a wind directions. Excuse me. Do you have a question, André? Or maybe can you mute your mic? Thank you. So yeah, so I continue. So we have a surface pressure. So it is the atmospheric air pressure reduced to mean sea level. And we have direct radiations. So the direct solar radiations are computed as an average of the preceding hour on the horizontal plane and the normal plane. And we have the diffuse radiations, also an average of the preceding hour. And we have the cloud cover percentage. So we use a mean of a total cloud cover as an area fraction, but as cloud covers, we have the clouds between 0 and 3 kilometers above ground. Then we have between 3 kilometers and 8 kilometers for the mid cloud cover, and for the high cloud cover, it's above 8 kilometers from the ground. So with OpenMeteo, you can use its API, it's open source. You can go on OpenMeteo website and click on API forecast, and you will find the same curves I show you there. So you can plot, of course, the temperature and variations. In OpenMeteo, we have, so as I mentioned, the 4 types of meteorological data. In OpenMeteo, you have different API, and I put you, for example, the forecast API, which can provide hourly forecasts up to 16 days. But depending on the level, you have, depending on the model, sorry. So you have examples of forecast model at the bottom of the slide. So you can see it's not equivalent. You have the second one, which has forecast length of 16 days, but it can be less and can be not more, because this is the maximum, but it can be less. Then we have a historical API. So we have some data every hour that can be found until 2000. And there you can go far to 1950, but more you go to the past and more you will have details or a lot of variables. Okay, that first exercise. And then, so to retalk a little bit about the model with a mesoscale forecast model, which is a coupling that we are doing with another pilot of HiDALGO2, and where we have a grid, a resolution, a 2D grid with a resolution of 1 kilometer square, for example. We can have this type of meteo data. So here I put you a 2-meter air temperature above the ground at 1 hour. So here is 1 p.m. And this is the region of Strasbourg. So Strasbourg is there in the yellow center, and you can see the different temperatures variable in the same region. So it can stay the same in the city center of Strasbourg, but Strasbourg is a city which is it is very large from the south to the north. If you follow my cursor, it can start there and it goes until there. So it is quite large, and in some environments of the city, there is some differences in the temperatures. And you can see also when you go outside the city and you go to the campaigns in the villages, the temperature is less high. So that's why it's important. It can be very interesting to have more precise model of weather data. So yeah, here is the map of Strasbourg. So it is in the eastern France, and I put you an example of a 2D grid with 1 kilometer squared approximately. Okay, so let's go start the first exercise of the day. So it's about annual weather analysis. So we have provided you with a data set containing 2 cities. So you can view the weather data in various graphs in the notebook weather. And we will observe the data and answer the question. So the first question will be to look at the different weather plots to manipulate the data. You can change the different the different type of display, because we can display every hour the value of the weather data, but we have also a mean for the daily. We have a daily mean and we have monthly mean also. So to answer some questions, it will be very useful to use sometimes the hourly variables, sometimes the daily variables, and maybe the monthly variables. So the first question will be to just observe the data and try to explain the difference between the two cities. And I put an indication, so you can also you can rely on the temperature curves, but you can also look at the solar radiation or the cloud covers, for example. And in question 2, we will try to estimate a period where it is useful to activate the heating systems in the buildings. So let me show you again. So we will do the exercise in CodeSpace. So we will open it again. I will put the link for you if you are a little bit lost. I will do the same. I have to open CodeSpace. So did you open CodeSpace like yesterday? I put the link of a public organization of HiDALGO2 for training on GitHub, and you can go through the repositories and find your own and open it again with CodeSpace. So on my part, I can retrieve mine. So there it is. And let's open CodeSpace. Okay, so I can click on this one. So if you have any problem, please feel free to ask in the chat. Answer to question 1. Okay, perfect, Bart. I will close Ktirio, I will close some of my windows that opens. I will close this one. I will close Paraview too. Okay. So visualizations, I close this one. So there we go in notebooks. So you have training day 1, training day 2. So you go in training day 2, you have the weather notebook. So don't forget to select a kernel. So same as before, so Python 3.12.12, and normally the notebook should be executed file. So let's wait just like 5 minutes for you to manipulate the data. So I continue to share my screen. I know. Does my share? Oh, yeah, I'm sharing my screen. So you're seeing CodeSpace, right? Gwendolyn? I'm sharing CodeSpace. Yeah, okay. So you have the plot for city 1 and then for city 2. So you have the graphic for the yearly temperature evolutions. So here we have the hourly variables. So you can read a little bit, but you can zoom also if you want on a section, like from January to June, for example. You can see the peak. You can also see the dates at each point with the temperature. I can also move from hourly to daily mean. So in green, I'll close this one. So in green, you can see the mean daily temperatures. In red, you have a maximum temperature registered for a day, and in blue, you have a minimum temperature. And you have the same, but for each month. So here it starts in December 2023 because I think there is one time step at midnight or 11 p.m. But yeah, so you have the mean for each month. Also, you have the solar radiation analysis graphics. So you have the diffuse radiation in yellow. You have in orange the direct radiation. And in red, you have total radiation. Total radiation is the sum of the diffuse and direct radiations. So here it's quite hard to read something, but with the hourly variables, you can zoom, and it will be very interesting when you zoom to see it because you see the peak at each day. So here when there is no radiations, it's during the night, and you can see the curves are increasing during the day, and we reach the top when we are at 12 a.m. Here it's 11, here it's 11, it's 12, it's 1 p.m. So if I zoom on the first day, I can see so the total radiations is cumulative of it's the sum of the direct radiation and diffuse radiation. So here it's during the winter, but if I go during July, we have higher peaks. And also, so you can change and see the daily means and the monthly means. So I didn't put the minimum because the minimum will be always 0, so it's not useful to print it, to display it on the monthly and daily means. Then you have the relative humidity, which is plot. You have a mean of the wind intensity and frequency for a city during the year. So it's a cumulative plot. So we can see in this city, there is a lot of winds coming from the south. There we have a cloud cover. So cloud cover is also hard to read in using the hourly variables, but you can zoom on it. So for I will put the monthly up. So for monthly means, and for a plot of cloud covers, so you can see in black the low clouds, so which are near the ground. So we have the mid clouds in light gray, and high clouds with a lighter gray. So it can be very interesting to see also the monthly means. And there we have the pressure at the surface. So does anyone has an explanations to explain the difference between CT1 and CT2? Put a message like Bart in the chat if you succeeded or if you understood. If you have any problem to manipulate the data, feel free to ask me. So let's wait 1 minute. Oh, yes, that's it, Daniel. So it's different hemispheres. So the winter and summer, the seasons are inversed. So the CT2 is from the south hemisphere, and the CT1 is from the north hemisphere. Sorry. So you can see Paris. So this is the city of CT1 is for Paris, and CT2 is the weather for Sydney in Australia. And we can observe higher radiation peaks in Sydney. Here we have Strasbourg, the top, it's at 100 watts per meter square irradiance. We can see the monthly means compared to Sydney. His top is approximately 200 more. So Sydney is more exposed to the sun than Strasbourg. Different wind condition also. As Sydney is near the sea and the ocean, we have more wind, I think. It's one of the explanations. Okay, so now can you answer the question 2? For example, if we take a base temperature of 18 degrees Celsius, let's try to identify for how many months it is required to activate the heating systems for ideal and optimal comfort. You can put a message on the chat, put your estimation for Paris in Sydney. For 18 periods. Maybe. So let's give us 5 minutes, and after we will continue the presentation and do the exercise 2. So you can insert an estimations as you see. Sometimes we have mean temperature during June of 23, and so like 1 week after we have mean of 16.25. So let's choose the first date and the last dates where we have a mean temperature of 18. So if I do it for the Strasbourg curves. I think I will find it the 18th of June, maybe before. Before. So we have May. We have the 12th of May. So yeah, we have to answer the question for an optimal comfort, but of course the comfort depends of each person's. We don't perceive the comfort and the ideal temperature for every person is different. But yeah, let's choose the first date where we have 18 degrees Celsius of mean and the last of the year. And put your response in the chat under my last message. Okay, so we have a response from Bart. So Bart propose Paris 23 September to 30 June and Sydney 1 May to 20 August. Okay, so let's see. Yeah, you started. Okay. Yeah, because we start from January to December, but yeah, we generally start to heat in autumn. So let's check. Let's check the response of Bart. So September, you said 23. 23. Yeah. 23, we have max. So you have 15.3 mean. Okay. So, okay. So the mean, okay. 22, it's approximately 17. Okay. So yeah, it's quite fine. And June, I think we can, okay. Yeah. The mean temperature sometimes is 12 at the beginning of June. So yeah, I understand. But you propose 13th of June to deactivate so the heating systems. It's quite good. It's quite good. Well, I think we can do it even earlier, as I mentioned, maybe in May. So yeah, it's not so easy. So we don't deactivate for 6 months the heating systems. Sometimes we can reactivate it. But okay. And in Sydney, Sydney, we have, okay, so I have it, there it is. Sydney, you propose, so it will be easier maybe because the winter is at the center. Let's check the daily mean. Okay, so you propose 1st of May. 1st of May. Yeah. Okay. We have a mean of 14.85. So I think it could be earlier, maybe in April. Yeah, we have some mean at 18. Let's check April and May. Up. So at the end of April, we have a good mean and max temperature. Okay. So we can wait a little bit, but maybe we can start to eat. Yeah, it's while too here.
So you said the 1st of May. Yeah, it's quite good too. Yeah, as I said, we have a peak at the end of April at a mean of 18.83 and maximum of 25 and minimum of 15. So yeah, the 1st of May, it's a good response. We can see we really go under the 20 in this section. So the 80 is approximately there too. And the end, the 20 of August. So we at the start of August now we have mean approximately around 10 degrees, and yeah, it's increased a lot. So you see the 20 of August. Yeah, we have good mean to 16. Yeah. Surely we can stop the radiators at this period. Yeah. Yeah, we can deduce that we have better winter conditions in Sydney compared to compared to Paris. The winter is less long. Yes, as I mentioned before, it depends of the persons, the comfort indicators. Okay, so let's go again in the presentations and then we will do the exercise too. So, we'll give the mic to Gwenole for the following slides. Oh, okay, so I'm ready, Gwenole. So when you want, I need my mic.
So we have seen during this exercise that we wanted to hit the building at different, starting a different day during the year, and we can stop it at another one. But actually, what we didn't mention during this exercise is that we don't take into account the thermal mass of the building. And so actually, in the real world, we start hitting, so I will take France as an example because it's the country that I know for the regulation, but we start hitting during the 15th of April, and we stop hitting during the 15th of April, and we start again the boiler during the 15th of October. And the reason why is because even though we have some lower temperature, we can have some lower temperature during the summer, the thermal mass of a building, which will have received more solar radiation, and the outside temperature, the mean temperature during the month is much higher, and so the building will still be warm, even though the night could be cold. And I wanted to add a bit of trivia, since Bart mentioned that you can start eating a bit earlier if the wife is cold. The interesting thing about this is that it's a difference in biology, and so it's a question of thermal comfort. And once again, it's a question of heat transfer. And for women, they tend to have more vascular flow in the hand and feet, and thus the heat transfer between the blood and the ambient air is much higher for women in the feet and the area, thus creating thermal discomfort that is much higher for women than for men. And actually, for the first regulation, we set a temperature inside of 90 degrees Celsius, but it was for measurement that were done for men, and we didn't take into account women thermal comfort, and that's why it's preferable to heat buildings around 20 to 21 degrees Celsius if we want everybody to be happy. Otherwise, we will have only happy men. But I come back to the presentation. Regarding climate data, we have more and more with the rise of temperature. We have more and more heat wave. And so I wanted to give, we talk a lot about heat wave, but we rarely give a definition. So I wanted to give a brief definition of heat wave. And it's relative to what I talked earlier about building density. Because if a building have a high density and low insulation, they will have high inertia in contact with the exterior. And so heat wave is defined by a period of intense and sustained heat for both day and night over an extended period. So the actual temperature are region specific, but in the case of France, the daily temperature should be rising above 25 degrees during the day, and it shouldn't drop below 23 degrees at night. So we can see this as, it's obvious that we can survive a 25-degree heat wave, but actually the main problem is that it will last for several days, and the building won't go below temperature. So if we've got 25 degrees during the day and 23 at night, the building will be around 25 degrees even during the night, because we have high radiation from the sun, and the thermal difference between day and night is quite small. And so the building inertia will keep a lot of heat, and it will be difficult to cool down. And yeah, the impact of climate change is clearly shown since we have more and more heat wave, and we keep breaking record of heat wave duration and heat wave intensity. So in France, and I think it's true for many countries also in Europe, we had the 2003 heat wave. And it's an important heat wave that is mainly used in simulation. It led to a tragic excess of mortality around Europe. And it's revealed the high vulnerability of the building stock to extreme temperature. So the main interest of talking about this this year is, as we said previously, when we use when we simulate buildings, we use meteorological data that is either historical meteorological data or some formatted data. But when we want to use in our formatted data this type of heat wave to simulate our building in extreme conditions. And by that, I mean you don't aggregate data or you don't do averages, but you input the raw data for the duration of the heat wave directly into your meteorological data to make sure that you have a realistic simulation of an extreme heat wave. And so in France, we mainly use the year 2003. So in short, it's a safeguard to ensure that the new construction integrates extreme climate resilience. So for this, we have a quick exercise that is that resembles the first one, where you have to take a look at temperature graph and see when the temperature rises and doesn't drop below a certain point in Paris and Marseille. And yeah, if you can try and recreate what I just said about why it's dangerous for health to have such high temperature. Question 2 is also a question of common sense. So the main question is why in Paris this temperature rises remain significantly higher than the countryside. If you can try and so for those of you who don't know this phenomenon of the urban heat island, try to find some information about it and try to find some information that can justify this phenomenon. And yeah, the last question is also a question of common sense. Why the use of climate conditioning in buildings aggravate the heat wave response of the buildings that don't have any air conditioning.
So I will show you how to do it on the notebooks, but I think for most of you have found it. Let me find my code space environment. Up. Okay. So it's just after the exercise 1 in the same notebook. So you have the same questions that you saw on the slides. So you can respond on paper, on your desk, or you can create your own cell if you want in the notebook. And you have the same function than before to plot the temperatures. You can also choose to decomment. Okay. Yeah, I commented some of the function. Oh, I forgot. So verify the name of the variables, but you can print also the solar radiation, the wind woes if you want. It's not useful. But if you want to observe the meteo of Marseille, Marseille is in the south of France, at the bottom of France, near Italy. So you can plot and rerun again. It will work. Okay, and so you have, it's not the meteo of the year, but it's the meteo of summer. So we started in 1st of June and we are at the end of September. So try to identify the period of heat wave. And to do so, I advise you to use the daily mean. Try to find it for Marseille too. You will see Marseille as Marseille is in the south of France. The temperature are much higher and the heat waves were very, very intensive. As you can see the mean. Can you recall which the exact definition that we will use for this exercise, Gwenole? So Gwenole will write in the chat of Zoom the right definition we will use to do the exercise to identify the right period. So Gwenole put the definition. So the definition is 25 degrees during the day. And if the temperature doesn't decrease under 23 degrees during the night, then we have a day of heat wave period. Okay. So if you have an answer, please, you're welcome to comment under the comment of Gwenole in the chat. So you can put a response, approximately the number of days you can observe of heat wave period for Paris and Marseille. So Marseille will be a much bigger number of days. So let's wait just like 3-4 minutes.
So thank you, Maxime, for your answer. And it's quite a correct answer. I think that most important part in this answer is what you can observe is the duration of the heat wave. It was quite a long heat wave, and that's the reason why it was so deadly, because the temperature inside buildings really didn't drop below 25 degrees for a long period of time, and this affected greatly different countries in Europe. So, so the second question was, I will do the question in sequence. So if you had some time to look up a little bit about the urban heat island effect, we will go into detail about urban heat island during the next part of the presentation. And we will briefly talk about the third question, which is the use of air conditioning inside cities and why it worsens the heat island effect. But I want to do a more in-depth explanation just here during the exercise. Ouais, en vrai, tu peux passer sur l'explanation. Yeah, well, maybe I will do the explanation after introducing the heat island effect. This effect is quite common in big cities. So we call it an heat island because it's an island among the landscape, since cities are some clump of bâtiments surrounded by a vast landscape. And you can see that the temperature rises significantly around and is significantly warmer than the surrounding area. So this temperature difference is also more pronounced during the night. So the temperature in city drops less during the night than in the countryside. This phenomenon is primarily caused by several changes in the urban environment compared to the countryside. So the first one is the materials. So most city surfaces have a lot of asphalt and concrete, and concrete can absorb and store much more than solar heat during the day than the natural surfaces like grass and soil. And because they have a higher heat capacity and a greater absorbance coefficient, so an albedo that is less than the albedo of grass, they can store larger amount of heat from the solar radiation. The second effect comes from water and the lack of evapotranspiration. So cities have replaced the natural vegetation with impervious surfaces, and it eliminated the natural cooling that is produced by tree and plants, that is called evapotranspiration. So most of the plants tend to dry up during the day, and they store water during the night. So for water to turn from liquid to vapor, it needs to absorb heat from the environment. So when the water turns from liquid to vapor, it won't, its temperature won't go up, but it will still need some energy to break up the bond between water molecules. So it will absorb heat from the environment, and thus it will decrease the ambient air temperature. The third thing that you can find in cities is the urban geometry, where you have tall and densely packed buildings, and this creates urban canyons. So it will block airflow, and it will prevent the energy that is stored from dissipating, because it will restrict airflow. And last but not least, you've got the anthropogenic heat, so building, vehicles, and especially, as we said, air conditioning units. So you've got air conditioning units that are trying to extract heat from inside the building. But as we have to have a balance of energy, the heat that is extracted needs to be put somewhere, and so it's ejected in the outside environment. And when you have a lot of heat pump that are put on the facade and that extract heat from the buildings and have a bad coefficient, so they need to have a lot of energy to extract a small amount of heat. They tend to release a lot of energy in the urban environment. And thus, for buildings that don't have air conditioning, they are exchanging with a much hotter environment than if there were no AC units around. And so this response was the response to question 3. And now we can advance with the presentation. So we can advance with the presentation. The last part of the presentation will be still on Ktirio. So we have presented the workflow, how everything works together. And as we are doing a presentation on building simulation, I wanted to finish on the way we construct our thermal model and go in an in-depth description of the thermal simulation for Ktirio. So as we presented during the first day, the model that we use are multi-zone model. So we have one thermal zone per floor of a building. This primary objective is to calculate the thermal state of each zone, specifically the zone air temperature, and determine the energy consumption of a building. So this modeling choice of one zone per floor is pertinent for 2 key reasons. It's because we want to have the most thermal precision. So it allows us to capture the vertical thermal gradient, and we have better accuracy compared to a single zone model. So especially for the zone that are the top floor with the ceiling and the zone that is at the bottom floor, where the energy consumption will be much higher because you've got a greater surface area to exchange with the surrounding environment. The other reason why it's a pertinent modeling choice is that we are designing a simulator for city scale simulation. And so we have a lack of data. We only have access to the geometrical information of the building envelope with OpenStreetMap. And since we lack the detailed information of the interior layout, the one zone per floor approach represent the maximum and most relevant degree of precision that we can achieve regarding the input data available, because there is a parameter that is quite common for every building, which is the height of floor. So we know that for most building, the floor height is around 3 meters, so we can determine the number of floors per building using the outside envelope. So the model we use are some unsteady state model. So using a multi-layer resistance conductor model. For the solar gains, we have advanced radiation modeling using the Paris model that we introduced yesterday. And we use, and that's an investment regarding building simulation, because it's not widely used in the state-of-the-art software. We use ray tracing, as we have shown to determine the shading coefficient for each building. So also for window transmission, we calculate the properties of a window based on a number of parameters, and this allows us to have a correct transmission coefficient, which is based on some Fresnel equation and which is dependent on the angle of incidence from the sun. And we have a parameterizable window with a number of panes that can be variable, and it will automatically calculate the properties of the window. And we just have to input pane properties to calculate this. For convection and radiation, we do a precise calculation of convection using roughness of the wall, wind, but also, as we have seen, we can couple with CFD software. We want to couple with some CFD software, and we will have a very high degree of precision regarding the convection coefficient. Regarding infrared exchanges, currently we are modeling the infrared exchanges between the building, the ground, and the sky dome. But in the near future, we want to model the infrared exchanges, and we also, so of course, we also model infrared exchanges inside of the building between the different walls. But in the future, we want to model infrared exchanges with the surrounding buildings. So each building will have view factors of the other building, and it will have access to the wall surface temperature of each building that is simulated around it, and we will be able to have correct infrared exchanges between buildings. For ventilation, currently we only have single flow ventilation, so it's a constant air change rate, but we also want to change that and move toward a more complex simulation using some complex system with so double flow ventilation that will extract heat from the outgoing air to give it back to the incoming air flux. For climatic data, we have an extensive data set, as Philippe has shown you earlier. So regarding system and control, currently we can model buildings using ideal heating or cooling. So we will maintain constant temperature, but we can also have a control system on those ideal cooling and heating. So as we have said, we can shut off the heating system during the summer season and turn it back on. But we also have modeled some various heating system, and we also have modeled a boiler and a heat pump. So the boiler can only produce heat, but the heat pump system can produce heating and cooling based on the temperature difference between the exterior and the interior. We also couple the boiler to a radiator system to be as precise as possible. And so we simulate the flow of water inside the radiator to simulate the heat exchange. And we have a control system on the valve of the radiator to modulate the heat output of each radiator for each thermal zone. We precise everything in pre-processing in order to have a realistic boiler and radiator system because we could input a very high nominal heat output for the boiler and it will work, but it won't be as accurate because it will have a very high response to thermal changes inside the building. So we want to be as accurate on the nominal heat output to represent some gradual heat changes inside the building that can last for several hours when the building is not heated and we start turning on the boiler. And the control loop system is actually some PID controller that we have seen yesterday. So to make sure that our models are correct, we have done the first validation process that I introduced during the last course. So we had a look at our variables. We made sure that everything was dimensioned properly. And then to make sure that our algorithm and our equation were up to date with state-of-the-art software, we are currently benchmarking on best tests, and we have done the first test and the second case, which are case 600 and 600 FF, so for free float temperature. Those two tests use ideal heating and cooling, but they are used to make sure that we model the thermal behavior of the envelope of the building correctly. When we will move to case 900, we will make sure that we model the thermal inertia correctly. Same for 900 FF. And then we can move on to make sure that the heating system are correctly modeled also. And in the end, we want to take those case tests and directly implement them in our CI/CD pipeline to have reliable testing each time we make a modification on the building models. And so maybe we can start. It's 12:24, so we will start the exercises for this afternoon after the lunch break. So we can be back by 1:30 p.m.
Okay, so we will do some exercise this afternoon. I let Gwenole explain a little bit the purposes of the exercises. And after I will show you how to manipulate the notebook and what are the objectives in terms of coding to solve the problems.
So welcome back, everyone. So for this afternoon, we designed 3 exercises. So the idea is that you will have to optimize a building, and for each exercise, it's the same building but with more parameters. So the idea behind those exercises was we did talk a lot about thermal inertia, thermal insulation, the different kind of energy transfer. And I think that the best way to understand those phenomena is to actually put them in practice. And so the goal of the exercise would be to optimize the building and to obtain the minimal energy consumption for each building. So you will have a set of parameters that you will be able to modify. This set of parameters will be gradually expanded as we add more and more information into the model. So you can see for the exercise 1, it would be a simple building with no windows for walls. And the bottom would be connected to the ground temperature, so constant ground temperature. For exercise 2, it will be the same building, but this time we will add windows, and you will be able to modify some parameters for the windows. And finally, for the third exercise, we started adding more thermal zone to the model. So it would be a building with a gable roof. So we will have 2 thermal zones. One would be the initial building from exercise 1 with the windows. The second zone will be right below the roof. And so the first zone will be heated, and the second one be below the roof won't be heated. So you will be able to test some different strategies. We did a lot of writing inside the notebooks. So I advise that you take some time to read those information before jumping into the exercise, because we give you some hints on how to optimize the buildings, and we explain the different variables that you will be able to access. So what I want you to do for those exercises is, if you can and you think that you've optimized enough the building, you can input in the chat the final energy consumption of the building. So it would be the value at the end of the curve. We will be simulating the building for a 1 year period. So you will have to optimize the building for the winter time, but you will be also careful because, for example, if you put big windows to optimize solar gain during winter, you will impact the cooling load during summer, and it will negatively impact your energy consumption. So you will have to play with those two energy consumption, so the heating part and the cooling part. I think I will let now Philippe introduce the notebooks, and I hope you will have some fun trying to optimize those buildings. At least I know I did have some fun trying to build this exercise.
Okay, perfect. Yes. Okay. So I close the wind weather notebook. Okay, so we can open the case study number 1 notebook. Okay. I think you can start running the cells if you want. Even the results we see at the bottom of the notebooks will not be fine, because you have to change some parameters. So there you have the questions and the guide through the exercise. So as Gwenola said, your goal is to optimize the building design parameters, so the geometry, the orientations, and the material properties, to minimize total energy consumption, while maintaining the thermal comforts within the habitable zone. So you will have to heat and maintain a temperature degree of 20 degrees. So I will let you read the entire text. I will come back to it after, but we can quickly read together the exercise. So you have learning objectives, and so there it is. So you have the building configuration and constraints. So you have the geometric constraints. So you have to have a ground floor area of 100 meters square. So basically, we have a building with 4 walls, and the 2 walls are parallel to each other. So you just have to imagine a rectangle or a square. So you will have the length wall 1, which equals to length wall 3. And in the same time, you will have length wall 2, which is equal to length wall 4. So respectively, the values to have a rectangular shape. So you can change the configuration. So You can start with 10 meters square by, you can start with 10 meters length for each walls. So you will obtain 100 meters square, but you can change and use other values if you want. So if you want to optimize, for example, the solar radiation received on the south or the south surface, you're welcome to adjust as you want the orientations and the length of each walls. So the height of the walls and the building must be between 2.7 meters and 3 meters. You can change the wall orientations. So it's not very useful because you always have I don't know, sorry. Basically, it's oriented to the south, the west, the north, and the east, but you can adapt to have walls oriented to southwest, southeast, etc. So you can vary. You're not you can put other values than 19, etc. But when you will change one azimuth, the rest of the azimuths will change to keep the rectangular shape of the building. Okay, so then you have the material and construction constraints. So every opaque elements, so wall, roof, and bottom ground, must consist of 2 layers. So you will have an interior layer and an exterior layer. So you must use one heavy material and one light material. I will show you where I will show you 2 dictionaries of materials that we will use for this exercise. So we put you some constraints about the total thickness. So the addition of the thickness of the interior layer and exterior layer of each wall must be under 0.40 centimeters, right? So you can, for example, choose 10 centimeters for the interior walls and 30 centimeters for the exterior wall, but or 20 as you want. Then you will have to choose, so as I said, one light material and one heavy material. So one light material is for the insulation. So you can choose if you want to insulate from the exterior or the interior. So you will find in the sources in cube course similarly, you will find a file named materials.py which store a structural materials dictionary and an insulation materials dictionary. So here you have descriptions of each materials, and you have its thermal properties. All right. So this file is imported in the notebook. So here you have the simulation plot factory to simulate the to plot graphs from result of your simulation. You have the weather plot factory, and you have the FMU simulation class to simulate. I forgot to put the import for the material, so you can do in the same time with me. So you can do from cube.course.simlib point simulation. No, sorry, from materials. You can import basically the two Python dictionaries. So you can put structural materials in insulation materials. So if I execute, it works. Okay, so you can create code cells and you can basically print a structural dictionary. I think, yeah. So you see those values, right? They put reinforced concrete. Yeah, it will print the value for the reinforced concrete. So then you will have to pick those values, or using the dictionary, you can directly attribute some values for the building parameters. So I will present the variables for the building parameters. Right. So, as we said, the objective is to minimize the energy consumption in total. So if I go to the exercise, so you have the weather which is displayed. It's the weather for the year in Strasbourg in 2023. Basically, you will use the same graphics that we used this morning. So you can see the temperature curves. You have the daily means and the monthly means. All right. If you want, you can plot, for example, the solar radiation. So if I play again, I will plot the solar radiation. Okay, let me just check the chat to have it. Okay, and then you have the building thermal simulation part. So you have function to fill. So we have two functions. We have a function to calculate a wall resistance, and we have a function to calculate the total heat flow balance. So then you have instructions about the name of variables to use in the code. So you have the building element thickness, so the thickness of the wall, the thickness of the roof, so interior and exterior layer at each for each element. You have a ground slab. You have material properties for building elements. So I put only the lambda, but I think I forgot to put the conductivity. Maybe that's a little mistake. We will give you the, oh, but it's there, okay. You have all the parameters there. So I forgot to put it there, but here you have a dictionary with your inputs. So there you can modify as you want the thickness, all the parameters, the length. So we put 10 by 10. You have a 10 by 10 values for the length. You can modify the length, the height. You have absorption, the surface absorptivity. So you can modify as you want. For example, I will put there this, put 0.3, etc. Here you have some variables to modify the heating and cooling powers and the air change. So this variable, you just have to modify it with the value you will compute to find the right maximal heating power necessary to heat the building as you want.
here is a cell for the variables we want to display in the graphics. So if there are some variable missing, we will add it. Then you have a simulation cell. So basically we instantiate a new FMA simulation, and then we initialize. So we put a start time at 0, and we put the number of seconds for 1 year, and we have a time step, so 1 hour. And then you have the function to simulate. In the function to simulate, to run the simulation, we put the list of variables we want to print after. So finally, we have a plot. And you can plot the evolutions of temperature. So here we have the external temperature and interior temperature. So here it's quite the same because I didn't put really heating power. So it's normal. Again, okay. So like this should be fine. Okay. So don't hesitate to put this sign to avoid to have two graphics, two same graphics. So then you have the plot of the convective coefficients, which are important to use for computing the resistance. Then you have your plots for the energy consumption through the entire year. So here I don't hit a lot, but it will increase much more when I will add some heating power. And then I put the X-flux exchange between the exterior surface and the environment for each walls, and the heat conduction across the exterior layer. So let's add sign up. Okay, so first of all, maybe you can fill the parameter first and choose the materials that suited you. Let's choose for which layer you put the insulation and the structural materials. And you can start, if you want, to put much more heating power. It's just to give you some new results on your graphics. But after you have done that, you should fill the functions that we gave you. So I see there is a question in the chat. Maybe we put an error. Okay, I will check that. Maybe Gwenole, if you can explain about the computation of calculate the wall resistance, if you want to add something as you wish.
So for this, please feel free to reach out to us if you have any difficulty or if you need any reminder on the way we calculate resistance. The idea is, as you will change the value for the different walls, you will be able to calculate each time the correct value for the heating power. You still can do the exercise if you are not really interested by these parts, but it will be better if you do it because you will have accurate boiler sizing Whereas if you want to skip this part, you will have to input a very high value for the boiler, and it will degrade your simulation because it won't be as close to reality as the correct sizing of boiler.
So yeah, the results of the example should be 0.318 kilometer per watt. Yeah, not kilometer, sorry, Kelvin per watt. Okay. Can you pass the imported line in chat? I got the importer of the wanted. Oh yeah, okay, yeah, of course. So I will write every code cells if you want. If you have any problem, I will help you. So let's start with the import that is missing. So I will put it there up, and I will put the explanation. So to import materials, dictionaries. Okay, so Andre, I put you the line in the chat. We can put it under your comment too, like this. Okay, so from my side, I will do the exercise slowly, and I will keep to share my screen. If you have any questions, feel free to open your mic if you want, or to ask some questions in the chat. Yes, so where you have to put your data for wall and azimuth code. Okay, so if you're in the notebook, case study 1, you should go. I'm not sure, but maybe there is the outline. Yeah. Okay, so if you open your Explorer of file on the left, you will have the summary. So there you can go to exercise resolution and go to building thermal simulation. So you will find the function you have to write. But first of all, I'm waiting. Okay. When you are in the building thermal simulation, you can go down. You can come down until you find simulation and graph display with names of variable to use in the code. And then you have a little bit of explanations, and you have the code cell with the input variables. And this is here that you will put your values for the properties of your walls, the thickness, the absorption. So I didn't put the azimuth, I think. So Gwenole, maybe we can share the name of variable, but first of all, it's not so important to change the orientation. First, you should just assign your thickness. So from my side, I will put 10 centimeters for my thickness of my interior wall, roof, and bottom. And I will put 0.3 meters for my exterior layers. And then I will use the same materials for the ground, the walls, and
and the roof. So I will use reinforced concrete for the exterior part, and I will use rock wool for the interior layers. Then I will put 10 meters for the length of wall 1 and 3, and 10 meters for length wall 2 and 4. So did you find the code cell? So we'll check. So you reproduce what I'm writing right now? I can stay on this cell, and I can go slower if you want. Renouvellement d'air, je mets à zéro. Okay, so let's put 0.5. So Maxime, we are using just the physical model part. We are not using the mesh. We are doing some improvements in Ktirio to do some simulation of one building using the same computation code that we use for city scale simulations. But right now it's not ready. We are improving it by developing some binding functions to use the C++ code in Python. But right now we just use the FMU part, just so the physical equations. We are not using a mesh. Yeah, Vulkan, I will change. I will check if azimuth full one is correct or not. So yeah, concerning the azimuth variable name, I think I didn't put the very last version of the FMU model, so there is a little bit of errors in the name, but we will change it. But let's stay with the basic configurations. We will change the azimuth after. I think in the second FMU it will be better because I'm pretty sure I put the very last version for the second FMU. So I have the variables. Let me up. So I will put the azimuth there. So the azimuth. So here we will put, for example, 0 for the south. And then we can put like oops.
You have to select the materials that suited you. So you are free to choose between the 10 materials of structural materials, and you are free to choose the insulation you want. So I don't remember exactly the list, but we will show it. I will come back to this just after. So here for structural materials, we have reinforced concrete, hierarchic concrete. So you have small descriptions if you want there. We have brick, we have over concrete block, granite stone, limestones, oak wood, pine wood. And for the insulation, we have glass wool, rock wool, polystyrene, some type of polystyrene, dense wood fiber. So we put very large, you have a large choice to choose the materials you want. Where are the materials? Yeah, I can show it again. So maybe, yeah, if you tape on your keyboard, that's the right one. If you do Control P, Control plus P, you will have this searching bar, and then you can enter materials and click. And you have the path. So materials.py is stored in source files, Python, cube, course, simlib, simulation lib. So basically, I can write it in the chat. Okay, so I have the correct variables for the azimuth of the walls. So excuse me for this mistake. So I will put it in the chat. Oh, okay, I mistake. I didn't put the comment in the chat. Sorry. Okay, so walls. Okay, so I put the right name of the variables for the azimuth angle for each wall, and I put a message, so please sure there is a 90-degree difference between each wall. So normally for the exercise 2, we will not have this problem, it will be easier. But yeah, I sent the wrong message. So if you are looking for materials.py file, you can press Control plus P to print the searching bar, and then you can enter the name of the file you are looking for. So I do my simulation. Okay, so it's a success. So now I will print my new results. Okay, so there I have a temperature stable at 20 degrees Celsius. Okay, that's for sure. I put too much power. You have mirror, okay. Say with two O, so rock wool. Yeah, thank you, welcome. Okay, so sorry. So this is my evolution of temperature, and we will show the energy consumption over the year. So, okay, so now I'm at approximately a total of 53 kilowatts per hour. Okay, so now we will try to reduce this value. Okay. Wait, yeah, I don't have cooling right now. So if I put some cooling power, just I will put 10,000 to up. So let's run the simulation, but with cooling power. Okay, so we have no differences because we are under 24, so the cooling is not active. Okay, so I will check. I will go to fill these functions. So we will fill the exit wall resistance function. If you have some results, feel free to put your score of total energy consumption at the end of the year. If you have already some results. Okay, so Maxime has a first response. So you have a total energy consumption over the year of 18 kilowatts per hour. So yeah, very good. Let's try for us to do the same or better. My indoor temperature is not set like your. Okay, I'll check. You mean the temperature is not staying flat, that one? The red one? So how much power did you put for this variable? I will show you. Oh, sorry, it's there. So the heating power is there. So yeah, this is this variable that you have to change when you find the right total power to. So because first of all, you can just start. I can just put a lot of powers, and I'm sure I will hit. But then the objective is to reduce this value to just have the minimum of the power needed to hit sufficiently. Okay, so perfect. So okay. Variable azimuth wall not found in the. Okay, so Andre, let's come back to the cell because I did a mistake. So I think you keep the azimuth wall. I put the azimuth variable I put there, but let's delete it. All right, let's delete it. And so for this exercise, in the second, it will be easier normally, but you have to put this one. So these 4 variables. So please be sure to change to have a difference of 90 degrees between each wall. So, so this is the south. Normally is the west, I think. North. And east. Okay, perfect. So if you can correct it, it's fine. Yeah, it should match. Yeah, it should match the input maximum. Sorry, the notebook is not fully automated. So yeah, you will have to change by hand. Yeah, maybe there is some automated computations of the height. I'm not sure. But if you want to be sure, let's keep the same values that you put there in your function. Or I think maybe when you call your function, you can use inputs and you have the height. So if you want to don't repeat yourself with the values, you should call your function of computation of wall resistance after the inputs initialization. There you can compute wall resistance and you call your arguments, the parameters. So I will start to write the functions. So if you found some new results for the other ones and Maxime, please, you're welcome to put a first score. I will put the first score I get, all right? So with no optimization. So total, yeah, so my first total consumption, 40, 54.
So I will do a brief explanation of what Philippe is doing here. So he's using the formula to calculate the total conduction. So as we are in a very simple case with only two materials for each wall, and those materials are put one after the other, we are in a case where we can have the electrical analogy that correspond to a series of thermal resistance. So the earth total will be the sum of each wall material resistance. So thickness divided by the thermal conductivity of the material multiplied by the area. And so what Philippe is doing here is adding them all up. And he will be adding also the convective coefficient to finally calculate the total resistance. So we already did the interior coefficient, and now we will do the exterior convective coefficient. What is kind of interesting in the example that we gave you is that you can see that our calculation for the interior coefficient is the same for every wall, but when we are calculating the exterior coefficient, it varies for each wall. That is because we calculate the exterior coefficient, convective coefficient, using the wind speed and the wind direction. So even though you have same surface area for the four walls, you will find different exterior convective coefficients, and that's because we are taking into account the incoming wind direction. And finally, we can see that Philippe has written the total formula for the equivalent thermal resistance.
So I will keep my screen during 3 minutes, and I will just beautiful the computations. I see Codespace is not very happy, but this one is correct. So please feel free if you needed to watch the function.
And if you want, we can do the same thing as yesterday. So we can have a look at the Modelica models that were used for these Python notebooks. So if you are interested, please tell me in the chat, and we will be able to do in the remaining time that we have left for the day, some presentation on the model and the way they are constructed, and you will be able to see a complete model of the building. So we won't have time to go over all the detail, but I can give you a brief overlook if you want. So yeah, please tell me in the chat if you're interested, and I will prepare something for the end of the evening.
So now we will write the calculate total heat flow balance function.
So what Philippe will now do is that he will use this function to calculate the equivalent resistance to start inputting the difference of temperature between the interior and the exterior. That will be useful to calculate the conductivity, the heat loss through the walls. And so the total heat loss will be a sum of all the heat loss through the walls. And it will be also the sum of the total wall heat loss plus the heat loss through ventilation. So air change. As we have an air change in volume per hour, we have to modify this air change to obtain cubic meters per hour, and then we can use the density of air to calculate some kilogram per second. And once we have kilogram per second, using the specific heat capacity of air, we can calculate the heat loss due to air change by multiplying our mass flow rate in kilogram per second by the specific capacity of air, so in joule per kilo per Kelvin. And then we just have to sum the heat loss through walls with the heat loss through ventilation. There is something that you need to be careful. The difference of temperature for the walls is not the same for every surfaces because we have the bottom surfaces that is in contact with the ground, and so the temperature difference for this wall will be different from the temperature difference for the walls that are changing between the interior air and the exterior air. So for the bottom wall, we have to use the temperature difference between the ambient air and the ground temperature. And once we have our total heat loss, that will be what we will be using to size our ideal heating system.
So I will use now the function that we have written. Just I copy paste it. And I will compute the wall resistance for each layers, for each walls.
So to explain why we made this, you write this little function, is that when we are simulating a city, we want to automatically size each boiler in pre-processing. And so we go through the different kind of heat loss in the buildings, we sum them, and we then apply this to size the boiler. And so for one building and one simple building, you could do it by hand, but when you start to have a huge number of buildings, it's quite useful to automate the process. And it will be even more useful when we will talk tomorrow about ensemble runs. And in that case, you multiply the number of simulation per buildings by the number of runs that you will want to do. And each time you will have to resize a building. And so you want to have function to do that for you. So what Philippe is doing here is he will be looking at the worst temperature. He notes the time and the day where this temperature happens, and then he will zoom on the convective coefficient diagram to have a look at the different convection coefficients in order to have a correct view of the different convective coefficients that he has to input in his function.
Okay, so the worst temperature is approximately at the 9th of February. It's approximately, yeah, minus 5.7. So I have to find the 9th of February. So I forgot to put the dates in the simulation plots, but okay. It should be approximately, which hour I put? Sorry, which hour? So which then 20, so 10 p.m. Okay, so let's have a look at it. So it should be approximately, so we have a score in seconds of the simulation. So it should be yeah, at 40. Okay. So I will choose a simulation. So I will put at 40. So the 9th of February is the 14th day of the year. So let's check the value. So so I rendered this value. So wall 1 H is 6.2 approximately. 2 H is 3.1. Wall 3 it's 3.22. Wall 4 is 6.2. And the roof is 1.7 in HI.
Yes. One. Let's just put one. So I use directly the values of the inputs dictionary. So I put inputs lengthful 1 multiplied by inputs 8. So for HE, I will put 1. For HI, I will put 1. For HE, I will put 6.2. And so the model layers, so let me remember what I put in it. So a dictionary with E and lambda, okay. Okay, perfect. Oops. Okay, so 1 layers equal that's equal. So I can put inputs. So I can keep the same because they have the same values. So layer 1. And then I can put so lambda int 1, and I can put so the thickness. How did I not that? Sorry. Layer E, okay. So E, I will put inputs, and I will put, that's right, yeah, E entire wall. All right. Let's get it like this, like this, like this, up. Layer exterior. On the inputs. On the exterior wall. And then I put E inputs E exterior wall. All right, and then I can close the dictionary, and it should be fine, like this. Okay. So let's try this one. Let's try to execute this function. Okay, so I put an error. String indices must be integer. Okay, so let me check. Ah, I know, yeah. I know why. Just let me print. No, I'm not sure. Let me print the wall with layers. Okay. So which mistake? Ah, it should be a list of dict. Okay, sorry. Each dict must contain E. Okay, so it should be a list. All right. Okay, so I just have to make a list with those values. Right. So here we have the first dict dictionary, and then we have the second one. Oops. Okay, so now let's check. Okay, perfect. It worked. Okay, so now I can do the same. So I will just change a little bit. I will put it in another cell. Whoops. Okay, cool. Right. So wall to resistance. So let's copy paste. So here I changed, so I called the function 6 times. So for the wall, it should be fine. Here, as I use the same materials of the roof, just to be clear, this could be it. This, and for the bottom, like this, but it can be different. We'll just copy paste first. That's our. Yeah, I just no, I can do it. Just let's write it correctly. So I copy paste, but I just have to change these names. So I put roof, and it should work. Roof, bottom there, bottom. Okay, so now I can be sure if I change the materials of the roof in the bottom, it will work. All right, so now let's change this value because this is the value for wall 1. So for wall 2, I had 3.1. So for wall 3, I had 3.12, 6.2 for wall 4, 1.7 for the roof, and we will put 0 for the bottom because it is in contact with the ground and not the exterior. That's it. Now I have to change the inputs. So wall 2 and wall 4 has the same length. So I put length wall 2, wall 1 and wall 1 and wall 3 have the same length too. So I put the same name. For the roof, I need the area, so I can just multiply the two lengths because we have a rectangular building. I can do the same for the bottom. Wall 2, and I can compute these values. All right. And then let's call the final function. Oh, okay. So calculates total heat flow balance. So we need the internal to exterior, air change. Donc là, so I take the air change of my inputs dictionary. So I put air change, sorry, there is a typo. It should work like this. Length 1, so I can put inputs, length wall 1. The same for this one, length wall 2, and there I put inputs 8. Okay. All right, so the exterior, so I have written, so the 9 February, the worst temperature was minus 5.7. We want to heat at 20 degrees. And for wall balance data, I think this is the list of all walls. Check the function. It's a dictionary containing the necessary data for balance. Each key is a wall name. Okay. We put the definition there, just to be sure. I can see the definition of function. It's weird. Okay. So, oops. So let's build the whole balance data. So it should be a dictionary. Each key is the whole name, so I can put the name I want, whole one, and the value. Okay. So in equivalence, so we put results before, and we have to return the delta t. So for the walls and the roof that are contacting with the exterior, so this is the difference between the walls temperature and the temperature we want in the interior. So basically it's 20 and it's minus 5.7. So delta T should be 25.7. Okay. Was it? Ah, that's it. I forgot 2 points. So let's copy paste it. Whoops, no. I just want this part. So we have wall 2, wall 3, wall 4, roof, and the bottom. So for delta T, it's the same, so 27, 27, and the bottom is in contact with the ground. So it's 20, I think it's 20 minus 8. It should be 12. I didn't verify if we put it on the instructions, sorry. Just let me check and we will compute. Yeah. Yeah, okay, so it's 6 degrees in the winter. So I think I have a little mistake there with prevent. Maybe I returned. We just want to float it down. Sorry. Huh? I think there is a mistake. Sorry for it. So yeah, there is a problem with Qvent. So let me check. Let me check this.
So yesterday I introduced a way to verify your calculations. So we will do a quick check to know which part of the formula is creating this problem. We will deactivate the heat loss through ventilation, and if he does the simulation, if he does the calculation again, we will see whether it's the ventilation loss or the wall loss that is causing a problem. And quite clearly, it's the way we calculated the heat loss which caused the problem.
No, it's Qvent. Okay, so yeah, there is a problem with the computation of heat loss for ventilation. Sorry for that. So let's check this value. Okay, so we corrected. Now we will check this value for the heating. So sorry, let me put it there in the heating power. And let's compute again. Oh, let's retry execution. So I have a little problem. I have to restart my notebook. Maybe it will be quick. Will take time. Sorry. Um. Okay. Let's execute it. Right. I have a problem with this cell. I don't know why. Okay, so as my notebook has a problem, I will restart it. So let's have a break and let's continue with a little bit of exercise. Sorry for these problems. So let's have a break and let's come back in 15 minutes. So like in 15 minutes, right? So I put the coffee break in the chat. Okay. So before, we found a value of 2,700 for the power. So we want to show you if we don't put enough heating power, what happens in the temperature curves. So let's display it.
So you can see the interior temperature in red. So if you don't input enough power, you clearly see that during the winter time, we have a problem heating the building at the correct temperature, and we are not able to maintain the set point temperature. But if we input the correct size for the boiler, which Philippe will now demonstrate, if we input the correct temperature, we should be able to maintain a 20-degree temperature, set point temperature in the building. And we will be able to see the importance of correct sizing for the boiler. So as I mentioned, the model that we are using are some unsteady state model. So we are taking into account the thermal inertia of the building. And what I demonstrated yesterday during the Modelica presentation is for unsteady state, we have to input a starting value for the temperature for the wall. So what we actually do in the Ktirio software is we change the temperature inside the wall to obtain a balance between the wall and the exterior. But if we don't do this calculation, the basic input is 8 degrees Celsius. So if we zoom at the start of the simulation, you can see that the interior temperature of the building is 8 degrees. And since we have inputted correct sizing for the boiler, we won't be able to heat the building directly, and it will take us some time to heat the building up to the 20-degree temperature set points. And you can see that it takes around 2.5 days to heat the building. It's quite the same thing for you. If you go on vacation and you leave your house, it will get cold since you don't have any heating in your house. And when you come back, it will actually take some time for the radiators and so for the boiler to heat up your home up to the desired temperature. And since we do a correct sizing of the ideal heating system, it will struggle a bit to obtain a 20-degree temperature right away. But if we input a very high value for the ideal heating flow, it will heat up quite quickly, and it won't be as realistic as this kind of simulation. So for the moment, we are not using any scenarios, but when you are using scenarios and you are simulating vacancy in a building, that's why it's important to have correct sizing for the boiler, because it produces some realistic results for the temperature inside the building. So maybe, Philippe, you can put a very high value for the heating system just to show that if the value is very high, we don't have as much, if you input, 20,000, something like that, the time it will take for the building to heat up would be quite quick. And if you zoom really, so yeah, you can see it's less than a day. It's really quick, and it's physically impossible because it will be like putting a small sun inside your house. So we don't want this kind of thing. We want to have realistic results, and so we need correct sizing for the boiler. So I think we can move on to the second part of the exercise. Maybe Philippe can give you the function he created to generate the sizing for the boiler. And I will let him take the mic if you want to present.
Yeah. Yes, so let's go through the second exercise. Maybe we will not have enough time for the exercise with the roof, but let's try. Sorry, it was my idea to put some codes to complete in the functions, but maybe it was not so useful for learning, so I apologize for that. I will show you and put it in the chat maybe if you want to copy paste. So just let's go just through the exercise, and then I show you I copy paste the functions you have to use. So there you have another optimization exercise. It's the same kind of buildings. We just have integrating some windows to the building. So each wall now have a window. So you have some constraints. So be sure to have a width for your window and a height for your window that is smaller than the length and the height of a wall. And so we will have the same constraint for the height, and we'll have new variables to manipulate. So we put the width window 1 and the height window 1, and you will have the same parameters. So normally, I think, yeah. So you have the same inputs than before. Just we had the parameters for the window. Here you are free to give the dimensions you want. So you can keep a 10 by 10 length for your walls with a height of 3. But you can choose for each wall which size of window you want. So maybe you will want to play with the solar radiations. So basically, I think the window 1 is oriented to the south. So maybe it should be interesting if your window is larger than the window 3, which is the north. So maybe we can put those kind of value, for example, and for window in the north, maybe I don't want to have a big window in the north, and for the others, maybe we put 3, for example. And for the height of a window, let's keep 1. Let's keep 1, so yeah. So I think you can
just copy paste the same thing you put in your case study 1. And so I will give you the functions for the computations of the wall resistance.
Cool. So I am currently uploading. So now it's done. You have a file, a Python file called functions.py in your in the chat. You can just download and copy paste the functions. So don't forget to create cells. So let's go through the so let's create a new cell in case study 2, and then you download the file. Up. Create functions, find Python, save. And then when it is downloaded, let's retake it. So
Ja, ça va être très compliqué. La fonction, il faudra juste inverser les choses.
so sorry, let's tabulate it. Wait, there is no tabulation, sorry. Up. Yes. Okay, now you should be fine. Up. Let's run all. Okay. Let's copy paste it too. Up. Oh. Okay, perfect. Okay, so now you can play again with the input parameters and try to observe what difference you observe with windows on the walls. And then we will try to compute the same way as before, but hiding the windows, the perfect heating power that we need. So let's wait 5 minutes and I'll let you 5 minutes working on that and I come back. Feel free to ask questions.
So we we gave you a function to calculate the thermal resistance of the wall, but it was a simple wall with 2 layers. And we will now have to change this function in order to include the windows. So if you remember correctly, last time during the course, I showed how we can add a window with a wall as parallel, as in a parallel circuit. So we have to make sure that the equivalent resistance that we calculate with our wall will be added to the window conductance by doing by putting the inverse of the wall resistance and adding it to the conductance of the window. So what Philippe is doing right now is creating a function that will allow us to add those 2 resistance in parallel. So he's defining the total conductance as the sum of the inverse of the resistance of the wall. So basically the inverse of the resistance of the wall is the conductance of the wall. And right now is also adding the exterior and interior convective coefficient to the conductance of the wall. You can see that he's not writing 1 over h. Since we are dealing with conductance, we can directly write h, and we don't have to do the inverse of h. Of course, as we are in a parallel circuit, we need to make sure we multiply by the area of the surface. And as we want to use directly the value we are calculating, we go back to thermal resistance, which Philippe called air equivalent total resistance. And he will be able to input this new resistance inside the heat flow balance, and we won't have to do any changes inside the function for heat flow balance, since we are dealing with thermal resistance. So maybe you can just change the name of this function to create wall resistance in parallel, since we are returning no wall resistance. Je pense qu'on verra. And with these small changes, we can now add the heat loss through windows with heat loss through the wall by inputting the new thermal resistance value that we have calculated. As you can see, for windows, we don't need the thickness or the lambda of the window, because when you are fetching information for window online, you will mostly see the U value, the total U value for the window, and they won't tell you the exact thickness or the exact lambda that is used to do this, to calculate this conductance. The U value for a window is dependent on the number of pane. So that's why you've got a single pane windows which have a U value that is quite small. But when you go up to 3 pane windows, you have a U value that is much higher. And the reason is because in between each pane, the insulator that is used for window is the gas that is located between each pane of the window. And it will provide a thermal resistance depending on the type of gas you use to insulate your window. The main problem being that the gas will evaporate at one point, and you will need to change your window to have good global performance. And so right now, Philippe is writing the information for the wall structure in order to calculate the heat flux, the total heat flux, and the change in heat fluxes between the first case study and the second case study. And he's doing a basic example using reinforced concrete and rock wool. For those of you who take a closer look at the material, you found that the best material to use for insulation should be the aerogel. And I think the best material for if you want to have a good thermal mass, it will be concrete, because concrete provides a high thermal mass. And the reasoning behind the way we look at insulation and structural material is we know that the structural material will have poor lambda value, so we will mostly focus on the rho and the CP value. And for insulation material, you will mostly focus on the lambda value. But as for now, I think it's useful to use a simple example with common material that are widely used in building. You won't find many buildings with aerogel because it's difficult to produce, and so you mostly find rock wool inside buildings nowadays.
So here I take the same value as I put in the case study 1, and we will compute the heating needed with our windows, and then we will plot the graphics, and then I will change the materials, I think, using the aerogel, for example, to have a better insulated building. So this is the same weather, so I think we can look at the 9th of February, and we will find the same parameters. So give me 5 minutes more. Okay, so let me zoom here.
So the graph that is displayed here only give you the exterior convective coefficient for the window, because the value are the same as in the previous case study for the walls, and we are only looking at the exterior convective coefficient for the new surfaces that we've inputted, so windows. And they are not the same as the exterior convective coefficient of the wall, because the roughness of the material is not the same. Thus, we are obtaining a different convective coefficient. Because as I mentioned earlier this morning, the way we do convective calculation is based on the roughness of the material. And if you have a high roughness, it will increase the heat exchange between the ambient air and the surfaces. And this kind of convective calculation are widely used in the state-of-the-art software. So the link between the roughness of the material and the convective coefficient is an empirical factor that was calculated in labs.
So I will compute the calculable wall resistance in the same way in the case study 1, and then I will calculate the wall resistance in parallel with the parameters of the window. So up. So let's calculate resistance in parallel. So I just have to put the one R equivalent that I computed before. So the U window is the input. So then I will choose, so let me check the parameters. So the windows area, so for wall 1, it will be input. So 8 window 1 multiply by equals to oops. So length, that's it. Width, okay. Width window 1. Okay, then we have the HE window. So for the window 1, I noted 4.84, and we need the H1, which is so then I do it for the 4 walls. And I will use 8 window 2, 3, 4, but they are the same. Here they are not the same. And here I noted 2.42, 2.42, and 7.46. But maybe this value will change because I change the dimensions of the width of windows. We will check after. Okay. So then we compute, so we calculate the total heat load balance. So let's take it, and now we will just use the wall resistance in parallel. The delta T should be the same. For the bottom and the roof, we have no change. Put inputs 2. All right. So let's check if I'm correct. Probably it will not be correct at the first shot, but maybe. Okay, so let me check if the convective coefficient were right. Yeah, let's see. Okay. Okay, so let's use this value as a heating power. And let's start a new simulation. All right. So let's plot. Okay, so it's pretty fine, but I think we have too much heat during the summer, but we are fine for heating during the winter. So maybe
So now we have a function to calculate the heat loss. We can reuse this same function to calculate the maximum heat gain during the summer. So we can do the same and just zoom on the temperature graph to see the exterior temperature during the summer and find the maximum value for this temperature. So if we want to size our heating system, we see that the value of 35.6 degree is the maximum during the summer. So to size our cooling system, we will just have to change the temperature difference inside the calculation for the flow. And we will calculate not a heating flow, but a cooling flow. And to calculate the temperature difference, so we have a maximum temperature of 35 degrees Celsius, but we don't want to cool our building to 20 degrees. We want to maintain a maximum temperature of 24 degrees. And so we have a cooling power that is 374 degrees.
so let's show the new results with the cooling power.
And so we can see that we maintain the temperature of at least at a maximum of 24 degrees Celsius during the summer. And if Philippe go down to take a look at the graphs, so encore.
The energy consumption graph is missing. I will add it. Sorry.
So we can see that now the total energy is the sum of the heating and the cooling. And you can see that at the start of the simulation, we are not cooling the building. So the heating energy used by the building is the same as the total energy. But as soon as we get to the summer, we see that the heating energy is stable, so we don't produce any heat and the energy consumed stay the same. But the total energy is increasing because during the summer we have the cooling flow that is increasing the total energy consumption of the building. We can see that the cooling doesn't represent the most part of the energy consumption, but it's still another form of consumption inside the building that was added with the massification of air conditioning and especially heat pumps. So even though it is not as great for a city like Strasbourg, it doesn't have the same impact as heating and the total energy consumption. What we have to see is that it's another form of consumption that was added. So as technology progress, we are adding more and more way to consume energy, and we can see this impact right here.
So just to try new materials, I will change the materials to take the better one.
Non, en fait, change.
Okay, so Gwenole is asking me to change the size of windows. So let's more see the impacts of a window. So I can put bigger one. So let's put 8 for every window. Let's keep it simple.
Je pense que tu vas faire ça.
And maybe 1.5 or 2 meters high. So let's keep 1 meters high. So let's see the total consumptions over the year and we will observe the difference. So we have a total of 49. I note it. And heating is 44, cooling is 5. So let's simulate another simulation with this kind of windows. Oh, before I forgot to compute the new total heat flow needed to heat and cool. Okay. Okay, so we definitely need more power. I hope this is not wrong. But no, I think it should be fine because the windows are bigger in summer, but so it should hit more.
So the reason why we have a much bigger, we need a bigger size for the boiler, for the HiDALGO2 is because the U value of the window is actually much higher than the U value of the wall. So window conduce heat much more easily than walls. And they are not great insulator, but they do provide the the opportunity to have solar gains. And we can actually see the impact of having two windows that are too large on a building. So even though it's quite useful for the winter, because as you can see during the winter, we don't consume nearly as much energy as during the last simulation. We can see that the cooling needs of the building have drastically augmented by a factor of 6. So we multiply our energy consumption for cooling by 6, which is quite huge. And in the end, it impacted the total energy consumption for the building. And we are actually much higher, even though we are consuming less energy during the winter. And as we have seen previously, the building used to consume a lot of energy during the winter. So what we have done here is we have made our building worse. And so sometimes you have to really refine your simulation to make sure you are using the correct amount of window, the correct materials for your wall, because one benefit effect during one part of a year can have drastic consequences during the other part of the year. So clearly, windows are very useful during the winter. They do have an impact because they insulate quite badly. So we have to size the boiler a lot more and do a bigger boiler. But that's because during the sizing part of the calculation, we don't take into account any solar gains. And so when we actually simulate the building, we see that when we take into account the solar gain, the heat loss is not as drastic as we might think during the winter.
So I think let's conclude the session. So we didn't work on the case study 3. I'm sorry for that. I should have not put functions to fill in Python. So sorry for this. Sorry for this mistake this afternoon. So let me stop sharing my screen. Okay. So this is all for today. So tomorrow morning, we will present you another presentations about the ensemble simulations that we run in using Ktirio Urban Building. So here it was a very simple optimization by hand. So it was a little bit hard. You have to change by hand every value. So tomorrow we will present the progress we have made in ensemble simulations. So those simulations will perform some optimizations for every buildings in a lot of with some scenarios. So we will have some parameters range for the thickness, for the materials, properties, and so on. So we will present you the ensemble simulations, and also we will try to perform for everybody. We will try to compute Ktirio simulations on Carolina and then analyze some results.